this is your opportunity to explore new ideas, maybe and even find inspiration for your studies or your research. Thank you all for being here, and special thanks to our distinguished guests for taking the time with us. Your reasons. Let's thank you all for being here, and special thanks to our distinguished guests for talking. Yes, okay. Yeah. Okay, thank you all for being here, and special thanks to our distinguished speakers and distinguished guests. And let's make the most of this day and enjoy the talks and discussion ahead. Welcome, and let's have a fantastic discussion today. Thank you. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you so much, Prof. Nuryani, for a warm and nice welcoming speech. It is true, everyone, that it is a great opportunity for us to have discussion from our experts, especially talking about catalytics, which I believe it's so familiar with us. So let's do not throw away this opportunity. All right, for our next agenda, we will have a token of appreciations. So maybe Prof. Nuryani you will give the gifts and also token of appreciation. Maybe start from Kamiya Sensei. Please, for token appreciation, please come forward, Sensei. This is as a gift from us, Sensei. Thank you for coming and sharing with us. Okay. We hope by giving this gift, it shows our gratitude to have you here. Okay, and please do the documentation. Okay, 1, 2, 3, cheese. Again, 1, 2, 3, cheese. One more time. 1, 2, 3, cheese. Okay, thank you so much. Thank you, Kamiya Sensei. Okay, for the next one, please, Prof. Nuryani, stay here. So please stay. We will continue the token of appreciation, maybe followed by Onoda Sensei. Please come forward, Sensei. Okay, another documentation. Please smile, everyone. 1, 2, 3, cheese. Okay. Okay, thank you so much, Onoda Sensei. Okay, thank you, Prof. Nuryani. You may go back. We will continue with Prof. Witri, perhaps. Thank you, Prof. Witri. Please give the token appreciation for next. Nakajima Sensei, please come forward, Sensei. Okay, another gift. Documentation, okay. Stand in the middle, okay. 1, 2, 3. Thank you so much, Prof. Witri and Nakajima Sensei. Okay. Okay, one more please stay, Prof. Witri. Okay, thank you, Sensei. You may go back. Thank you so much, Sensei. And then last but not least, for Otomo Sensei. Please come forward, Sensei. Okay. Ready? Take a photo. 1, 2, 3, cheese. Once again. 1, 2, 3. Okay. Thank you so much. Thank you so much, Otomo Sensei. Oops. Okay. Almost. Okay. Thank you, Otomo Sensei. And thank you, Prof. Witri. Okay. Okay, everyone. To complete our documentation session, maybe we can have pictures together, everyone, with Sensei. So we will have a picture time, take a photo for everyone. Prof, monggo Prof. Yeah, so many Sensei and Prof here. Okay. So we will have the Sensei and Professor first. Okay. Everyone ready? 1, 2, 3, cheese. Okay. Another pose maybe? Free pose? Thumbs up? Okay. 1, 2, 3, cheese. All right. Do we need to take with, okay, please, all the attendants, please coming forward. Kita foto-foto juga. Together with Sensei from Hokkaido University. Sensei and Professor, you may take back, okay? So everyone can join us. All right, everyone, please take a place. All right. Okay. Mas boleh tolong di foto? Ya, dihitung ya Mas. Another pose. One more time. Okay, thank you so much everyone. Give applause for everyone. Okay, thank you so much. We hope that the documentation session will be pretty nice, so will be remembered and memorized for all of us. And then for the time efficiency, maybe we will moving on into the main agenda of our session today. So we will have the first discussion. It will be led by Ms. Lina Mahardiani. And for the first session, we will have Professor Yuichi Kamiya with the topic of heterogeneous catalysts and also solid material for environmental science. And then continue with Associate Professor Ryoichi Otomo with the topic of biomass catalysts using inorganic compound materials. To Ms. Lina Mahardiani, time and place is yours.
Before you start, Selamat pagi, Assalamualaikum warahmatullahi wabarakatuh. Before we start, jadi sebelum kita mulai, saya akan memperkenalkan beliau dulu ya. Jadi I will read his curriculum vitae first. So his name is Professor Yuichi Kamiya. He is a professor in research faculty of environmental earth science, Hokkaido University. And for his academic background, he was graduated in 1997 from Department of Applied Chemistry, Graduate School of Engineering, Nagoya University. And then he got his PhD in March 2003, and he started his career as a researcher in Tonen Chemical from April 1997, and then become the assistant professor in Hokkaido University from March 2004, and he received his full professor in March 2015. So he also have some rewards. For example, Young Scientist in 2004, and also the Japan Petroleum Institute Award for Encouragement of Research and Development in 2008. And he published a lot of papers, maybe around 125 something. And his research topic is environmental catalysts for water purifications, catalytic chemistry of heteropoly compounds. So Sensei, you have maybe around 40 minutes. Yes, and the time is yours.
Okay, thank you very much, Dr. Alina Mahardiani. Selamat pagi. Nama saya Yuichi Kamiya dari Universitas Hokkaido. So, on behalf of the Hokkaido University and our graduate school, I would like to express our sincere thanks, especially to the Dr. Alina Mahardiani, to giving us this good opportunity to share our knowledge with especially the young scientists over there. So it's great honor and pleasure to give my talk. So in my talk today, I'm talking about the heterogeneous catalysis for purification of water polluted with nitrate. But before my scientific part, I'd like to talk about, I would want to introduce our university and our graduate school. So the Hokkaido University was established as a Sapporo Agricultural College in 1976. After that, the name and the organization a little bit changed. And in 1947, the Hokkaido University is renamed to current one, Hokkaido University. So Hokkaido University has a 140 years history. Next, please. So there is a map of the Japan. So the northern part, so Hokkaido University is located in Sapporo City. So the Hokkaido Island is located the northern part of the Japan. So the climate is a little bit cold and not so humid, but in winter, the climate is very, very severe, especially for Indonesian people. Okay, next please. Yeah. Next please. Already, okay. So we have, Hokkaido University has the 11 undergraduate schools, 21 graduate schools. So in the undergraduate schools from later education and pharmaceutical science and fishery sciences. So our graduate school is environmental science shown in red. So the Hokkaido University this graduate school and the undergraduate school covers all kinds of the science from social science and natural science. Next, please. Okay. So next, I would like to introduce you our Graduate School of Environmental Science. So our graduate school had 4 divisions. So one of them is the division of environmental science development. The second one is the division of earth system science. The third one is the division of biosphere science. The last one is the division of environmental material science. We are in the division of environmental material science. So environmental material science is based on the chemistry. Next, please. So our mission is the development of methodologies and materials for environmental remediation, including the water, air, soil, and the monitoring and the removal of pollutant from the environment, and production of the renewable energy and energy storage, so which are all based on chemistry. So for example, the research topics are decomposition and the removal of water pollutants. So this is my topic. The pollutant sensing, energy storage device production, and the production of new materials and green chemistry, and the biomass conversion. So biomass conversion is a topic on the Professor Nakajima's talk. So this is a good pictures to express the difference between the Indonesian climate and the Japan's climate. This is a photos of the Hokkaido University campuses. So Japan has 4 distinct seasons, and each season has different special colors. So for example, in spring, we have the pink, because this is a cherry blossom. Pink flower is a cherry blossom, which is a Japan national tree. So in spring season, the all cherry blossom is blooming suddenly. So the color suddenly changes from the white winter to the pink color. In summer, the color is green. The autumn color is red and yellow, because the color of the leaves are changed from green to the red and the yellow. So autumn is very beautiful season. So please come to Japan, especially in autumn season. Of course, maybe you want to see the snow in winter season, but I think winter is a little bit severe for Indonesian people. So Japan in autumn. Next, please. So there is a good picture. So this is a picture of our campus in winter season. So winter season, we have such kind of the snow on the ground. Next, please. But about 2 or 3 days in a year, we have the very heavy snowstorm. So after the heavy snowstorm, next morning, the car is fully covered by snow. So this is a very typical scenery of the winter in Japan. But you don't need to worry about it, because our government completely removed the snow from the road and ground, so we can smoothly going to somewhere by car next morning. So you don't need to worry about it. And winter is a good season for common tourists, and we enjoyed the winter season because we have the very famous and good festival, snow festival. So these statues and the buildings are made by snow. Of course, we cannot live in these buildings. We only enjoy seeing these snow buildings and snow statues. Okay, so now I'm going back to my scientific part. So I would like to talk about today is firstly the current situation of pure water. Of course, pure water is necessary for our daily lives. So I want to talk about the current situation. How much is the water is polluted, and what is the problem on the pure water for us. The second one is my research topic, the catalytic reduction of nitrate in water over the catalytic with special structure, random structure. The third one is the cascade process. Okay? Cascade process composed of ion exchange and catalytic reaction for purification of polluted water. So my topic is on the nitrate, okay, nitrate. First, let's begin with thinking about water. Okay, this is a good picture for us to have image on water. Of course, water, we need clean, fresh water to live, to manufacture industrial products, to grow crops, to raise farm animals. So it is apparent the water is indispensable matter for our sustainable development, okay? Sustainable development of our society, current society, and in future. However, we are now facing the water crisis. Okay? This is a figure showing the world population shown in the blue bar, and the number of people in the state of water shortage in pink bar, and the rate of people in the state of the water shortage, shown in the red circle and the red line. So as you can see here, now we are in 2025, so population is around 80 billion. But currently, around 3 billion people has a problem on the water, pure water. So this is a very big problem. And the United Nations expect the situation become worse. In 2015, almost 40% of people are in the state of the water shortage. So this is very severe problem. So now we have to start working on the ensuring. So how to ensure the clean, fresh water and develop the feasible technology to get clean, fresh. So groundwater is one of the most important natural water resources because groundwater has good quality and easily available and abundant and little change in water volume. So I'm not sure what the situation of the Indonesia, but in Japan, the last one, little change in water volume is very important. For example, if we take the water from river, of course, dry season, the water volume is very, very low. But normally, the volume change of the groundwater is only little over the year. So this is very important to supply fresh water continuously. So the effective use of groundwater is indispensable to develop a sustainable society. So point is how to use effectively the groundwater for our daily life. But now, the pollution of groundwater with nitrate is ongoing. Okay? Now it's a serious global problem. So why the groundwater is polluted with nitrate? So again, I'd like to show you the world population on the left side. So as I told you before, the population is still growing, and currently is 8 billion people is on the earth, and it is expected to much more increase. So which means more food is needed to support this population growth. So how to support? So how to make more food? So one of the technology is intensive agriculture. So to do the intensive agriculture, much more fertilizers are sprayed on farmland. Of course, the crop yield is increased. by the utilization of much amount of the fertilizer. But this fertilizer unfortunately caused environmental pollution. So one of which is the groundwater pollution with nitrate. So nitrogen fertilizer has the urea, ammonium ion, nitrate. But some cases, the organic fertilizer is used. So this compound has nitrogen atom. So in the soil, this nitrogen compound is transformed into nitrate, NO3 minus, by the action of the microorganism. And then finally, the nitrate, it reaches to the groundwater with the rainfall, causing the groundwater pollution. So nitrate itself is not so harmful, but if the people drink water with high concentration of nitrate is transformed into nitrite, and then nitrite, NO2 minus, is absorbed into blood, and then reacted with the red blood cell. So this red blood cell cannot afford oxygen anymore, so the cyanosis symptom appears. So this symptom is especially shown for the baby, an infant and fetuses. So this symptom is called blue baby syndrome. Okay, so now I hope you understand the current situation on water and how the groundwater is polluted with nitrate. So next step is the technology. So how do we purify the groundwater polluted with nitrate? So if this is a class, I want to ask the student, but this is kind of the symposium, so don't ask the student this question. So to think about it, the important thing as chemist is, firstly, we know the basic property of this pollutant. Nitrate is oxidant. Nitrate is anion, and nitrate is a kind of the nutrient necessary for crops. So, as a chemist, we need first and second property of nitrate, because nitrate is oxidant, so nitrate is reducible by chemical reduction. Nitrate is anion, so nitrate can be removed by ion exchange technology. Okay? So third one, so I will skip the third one, but the nitrate is a nutrient, so biological treatment is applicable. Okay, now the first one, chemical reduction of nitrate to decompose harmless compounds. So this is an example of the chemical reduction of nitrate. So for example, the nitrate, NO3 minus, is reacted with hydrogen gas to give dinitrogen molecule. So if this reaction proceeds, the polluted groundwater is purified, okay? But this reaction doesn't take place just by flowing the hydrogen gas into the polluted groundwater, because the activation energy is very high, okay? So the catalyst is necessary to proceed this reaction. So the other problem is water purification, which means the temperature basically cannot be controlled, because to increase the temperature of the water, much energy must be added to the polluted groundwater. It is not effective, okay, energy effective. So we have to proceed this reaction at around the room temperature. So this is very difficult as a chemical reaction. So catalyst necessary. So I'm sorry, so this is a high school chemistry. So what is a catalyst? What is catalyst? Catalyst is a material to increase rate of the chemical reaction, and catalyst is a material to promote only a specific reaction among the possible reactions. This is very important parameter, parameter as a catalyst, but remain unchanged after the reaction. So this is a catalyst. So I think the catalysts are excellent chemical tool for water purification. Maybe you are not so familiar with. So this is one example of the catalyst, platinum loaded on aluminum. Okay? So blue small dot is the platinum particles. Okay? So platinum nanoparticles are highly dispersed on the aluminum support, Al2O3 support. So catalytic reduction of nitrate in water was firstly reported in 1993 by German chemists. Okay? They firstly reported this reaction over bimetallic palladium catalyst. So the hydrogenation reaction of nitrate hopefully gives the dinitrogen molecule, and this is the desired product. But unfortunately, the ammonia is potentially produced by this reaction because of the hydrogenation reaction. Okay? So ammonia is unwanted product because ammonia has bad odor. So if much amount ammonia is formed by the reaction of nitrate, the treated water cannot be drunk. Okay? So we have to prevent the formation of ammonia as much as possible. So German chemists, applied the bimetallic palladium catalyst. For example, the iron palladium, cobalt palladium, platinum palladium, nickel palladium, silver palladium, and copper palladium. So this is their result. Okay? This is the decomposition rate of nitrate. Okay? So as you can see here, the almost only palladium copper system showed the catalytic activity for this reaction, nitrate hydrogenation. Okay? But important thing is the suppression of ammonia as much as possible. Next, please. So this is the selectivity to ammonia. Okay? So in case of the palladium nickel, the product is only ammonia. Okay? So the palladium nickel system is not good for this reaction. Instead, the copper palladium system, okay, this one, around the 70% selectivity of ammonia. Well, this is moderate. So this is not good, but this is moderate. But this selectivity is not enough for water drinkable. Okay? So selectivity should be further improved to suppress ammonia formation. So how to design the catalyst to suppress the ammonia formation? So we thought, firstly, that we have to investigate the two typical type of the palladium, copper bimetallic as a catalyst for this reaction. One is the left side is two components are completely segregated. So this is named here the segregated copper palladium alloy structure. The right one is contrary, the completely two atoms, copper and palladium, are mixed in atomic level. So this is named random copper palladium alloy structure. So we firstly investigated how the difference in the catalytic performance between the two typical structures. So the point is the preparation of the copper palladium bimetallic catalyst. Okay, copper palladium random alloy structure. So This is a preparation procedure for random alloy copper palladium particles. Okay? This is prepared by the reaction of palladium nitrate and copper nitrate in the presence of sodium citrate. And these two ionic species is reduced by the iron sulfate, so iron 2+. By this reaction, the very small random alloy copper palladium nanoparticles are formed. But in that state, the particle size is very small, so the nanoparticle is dispersed, so which cannot be used as a solid heterogeneous catalyst. So this dispersed copper palladium random alloy nanoparticle is supported on activated. This is a transmission electron microscopy images. So black dot is a carbon palladium and copper palladium nanoparticles spread and fixed on activated carbon. Okay, next one is a completely segregated structured catalyst. This is very simple. Initially, the palladium, only palladium nanoparticles is formed on the activated carbon, and then only a copper is supported on palladium catalyst. So by this reaction, the completely segregated palladium particles and copper particles are formed on the activated carbon. This is the typical catalytic performance of the segregated copper palladium alloy particles and the completely random alloy copper palladium catalyst. So gray bar represents the rate of nitrate decomposition. As you can see here, the random alloy structured catalyst was highly active for nitrate decomposition. But point is the selectivity. Okay? Selectivity difference is very significant, especially the random alloy copper palladium showed high selectivity to dinitrogen molecule. So under these conditions, the selectivity to dinitrogen molecule is around the 85%. But unfortunately, in these reaction conditions, about 50% ammonia is produced with about 50% selectivity. So we had to decrease much more the formation of ammonia. Next, please. To further decrease the ammonia formation is completed by the control of the reaction conditions. So normally we use the 0.8 hydrogen. Okay? So hydrogen partial pressure is a crucial parameter to determine the selectivity. So when the much more diluted hydrogen, so partial pressure is 0.05 atom, hydrogen is used, the selectivity to ammonia is almost zero. Okay? So by combination of catalyst design and control of the reaction conditions can achieve the highly active and highly selective reduction of nitrate into dinitrogen molecules. So next question is why such great difference in the selectivity appeared between the segregated structure and the random alloy structure. To understand the difference, firstly, we have to know the reaction mechanism. So the nitrate reduction proceeds successively through nitrite, NO2 minus, as an intermediate product. And the nitrate to nitrite is retrodetermining step. This step, nitrate from nitrite, proceed on copper palladium biometallic side. The role of the copper is stoichiometric reduction of nitrate into nitrite. As a result, the copper is into the copper. Instead, the role of the palladium is creation of dihydrogen molecule into the atomic hydrogen. After the oxidized copper species is reduced by with atomic hydrogen activated on palladium site to give the water to complete the catalyst cycle. Next, please. So after that, the night to light NO2 minus reduction proceed, okay, only on the palladium site. So in this reaction, the copper is unnecessary. So in the first step, the nitrite is activated on palladium site, and hydrogen, dihydrogen molecule is also activated on the palladium site. On the catalyst, on the palladium site, these two species are reacted to give the water and hydroxyl anion. And as a result, the atomic nitrogen and the atomic hydrogen are formed on the palladium site. After that, okay, if the nitrogen is reacted with hydrogen, ammonia gas is formed. Okay. But if the atomic nitrogen molecule is reacted, is formed. So this is the critical step to determine whether the dinitrogen molecule is formed or ammonia is formed. So now look at the case of the segregated structure. Of course, the nitrate to nitrite proceed at the interface between the palladium particle and copper particles. So at the interface, on the palladium side, the hydrogen and nitrogen are present. The copper side, basically the copper side is oxidized because of the stoichiometric reduction of nitrate with metallic copper. So only at the interface, the water is produced. So unfortunately, on the palladium side, the density of the atomic hydrogen is very high, which gives ammonia preferentially. So that is the reason for not so high selectivity to dinitrogen, rather selectivity to ammonia on the segregated structure, random alloy catalyst. On the other hand, in case of the random alloy structure, the copper and palladium site are randomly mixed, so that there are many the interface. Okay, please. So on this catalyst, the water produced at every position. The concentration of hydrogen on palladium site is low, so this condition is very good for the formation of dinitrogen. So that is a reason for high selectivity to nitrogen molecules over the random alloy copper palladium catalyst. I would like to change the topics. The third one, the cascade process. Okay, cascade process. Next, please. Okay, next, please. So as I told you so far, the catalytic reduction of nitrate is very good technology to purify the groundwater polluted with nitrate, because the nitrate is completely decomposed into the harmless dinitrogen molecule. But catalytic reduction of nitrate has disadvantage. For example, the formation of undesirable ammonia and slow reaction rate. Okay. Of course, to proceed this reaction, the catalyst is necessary, but even in the presence of the catalyst, the reaction rate, so decomposition rate of nitrate is still low, so which means large size reactor is necessary. And third one is the difficulty handling hydrogen molecule. Okay? Of course, hydrogen is an explosive gas, so it is not so easy to handle the hydrogen in water purification plant and common house. So there are three disadvantages on the catalytic reduction of nitrate. Instead, so there are other technologies to remove nitrate from polluted groundwater. Okay? So this is the anion exchange remover. Okay? So here is the anion exchange resin. Okay? This is just a resin. This resin has a quaternary ammonium group. At the quaternary ammonium group, there are the exchangeable, in that case, a chloride. So this chloride anion is exchangeable with other anions. So if this anion exchange resin is put in the polluted groundwater, the nitrate is removed by the action of ion exchange reaction. Instead, the chloride is released from ion exchange regime. So ion exchange advantage of ion exchange technology is rapid treatment and simple operation. Okay? So just putting the regime in the polluted groundwater to purify the polluted groundwater. This is very, very important for the large-scale applications. However, the ion exchange technology has disadvantages. For example, this is the only removal of nitrates, not decomposed. So we have to decompose nitrate removed from the groundwater in the next steps. This is a very good but very severe problem. And also the necessity of regeneration of spent resin. Okay? Anion exchange resin is not so cheap. So after the complete removal of nitrate, the spent resin must be regenerated. So how to regenerate the spent resins? Most simple way is the reverse ion exchange reaction. So if the spent resin containing nitrate is soaked in sodium chloride solution, the nitrate in the anion exchange resin is replaced with chloride. As a result, the spent resin is completely regenerated. But unfortunately, the waste brine containing high concentrated nitrate must be formed. So this waste brine is very hard to be treated because in that waste brine, the high concentration sodium cation and high concentration chloride ion are present in addition to nitrate, which prevent the further decomposition of nitrate by catalytic reaction. So the ion exchange technology is a very good method to remove and treat polluted groundwater, but the generation of waste brine is very, very big, severe problem. So how to regenerate the spent resin without the formation of the waste brine? So our idea is like that. If this reaction, this catalytic nitrate reduction takes place in the spent resin, of course, no waste brine is generated because, please, because spent resin is completely regenerated by ion by this reaction. Okay? But, so this reaction, if this reaction takes place inside the resin, the spent resin is completely regenerated. But the question is, how really this reaction proceed in the anion exchange resin? So to proceed this reaction in the resin, we think if the metal particles active for this reaction is embedded in the anion exchange resin, like that, that this reaction may take place even in the resin. So firstly, we prepared the metal nanoparticles embedded anion exchange resins So firstly, the metal anion, okay, metal anionic metal complexes, okay, is introduced into the anion exchange regime by anion exchange method, anion exchange reaction. Okay, after that, this anionic complex is reduced with dihydrogen molecule at 80 degrees Celsius to reduce the anionic metal complex into the metal nanoparticles. Okay, after that, the nitrate is removed by using this metal nanoparticle embedded anion exchange regime by a batch reactor shown in the left. Okay, at 83 degrees Celsius, the metal nanoparticle embedded anion exchange regime put in a solution containing the nitrate, 100 ppm nitrate. And then the anion exchange regime was removed from the solution. And then this anion exchange regime with nitrate is put in a flow reactor, okay? Right-hand side. And then the hydrogen gas was thrown into the reactor. And then temperature increased at 80 degrees Celsius for hours. Okay? So this is the removal process and the decomposition process of nitrate. So this is the metal screening result. Okay? Red bar is the nitrate, the amount of nitrate taken in the resin, and green bar is the amount of the decomposed nitrate. Okay? As you can see here, if the metal is absent, no nitrate was decomposed, even by the contact with hydrogen at 80 degrees Celsius. But when the metal nanoparticles are embedded inside the metal exchange regime, some of the nitrate will be decomposed. Okay? So if we choose the suitable metal nanoparticles, okay, if we choose metal nanoparticles, okay, and they are put inside the anion exchange regime, this reaction takes place to regenerate the spent anion exchange regime. Next, please. Next, please. Next, please. Okay, next, please. Sorry. So among the metals, gold was the best. Okay, gold was best. So we investigated and we optimized the amount of the gold in the anion exchange regime. So this is a relationship between the amount of the gold and the amount of the nitrate taken in the regime and the decomposed amount of the nitrate. As you can see here, the 0.3 millimole per gram of the gold was the optimum value. So in that material, about 0.3 millimole nitrate was decomposed, successfully decomposed. But if the excess amount of the gold was embedded in the anion exchange regimes, the decomposed amount of the nitrate is decreased. So this is due to the formation of the large gold particles shown here. See, it's the transmission electron microscopy images for the material with excess amount of the gold. Okay, as you can see here, the large gold particles form. So this is the reason for that decrease in the decomposed amount of the nitrate. So this material is reusable, at least for 5 times reuses. So this material is very stable for the removal of nitrate and decomposition of nitrate. Okay, maybe time is already coming, so I would like to summarize my talk. First one is, so I told about the background of my research. So groundwater is very, very important water resource at present and in the future. But now pollution with nitrate is a worldwide problem. Okay? The groundwater pollution is caused by human activity, mainly intensive agriculture. But intensive agriculture is necessary to support global population growth. So it is impossible to completely prevent the groundwater pollution with nitrate because we need more agriculture product to support the population growth. So we have to purify the polluted groundwater by some method, by some technologies. So we investigated the catalytic reduction of nitrate. This is one of the promising methods for purification of polluted groundwater. So highly selective reduction of nitrate into harmless dinitrogen molecule can be achieved by using precisely designed random alloy copper palladium catalyst and precisely controlled reaction conditions. And ion exchange removal of nitrate is another good method to purify the polluted groundwater. But generation of waste brine is unavoidable. So cascade process combining ion exchange removal and catalytic reduction is a viable method to solve the problem on the generation of the waste because this material can be regenerated even without brine. Okay, so finally I would like to acknowledge my colleagues and the student, especially the Associate Professor, Dr. Ryoichi Otomo, who is the second speaker of this symposium. And also I would like to thank our student. And also I would like to express our appreciation for the financial support from the Japan Science and the Promotion of Science. Japan Society for the Promotion on Science. Okay, thank you for your kind attention. Terimakashi.
Thank you so much, Kamiya Sensei, for your nice talk. But before we start open the discussions, maybe we can continue for Otomo Sensei to give talk. So please have a seat for a moment. Otomo Sensei, would you mind? Thank you. So before Otomo Sensei start his talk, I would like to introduce him. So his name is Ryoichi Otomo. You can call him Otomo Sensei. He was graduated from Graduate School of Science and Engineering, Tokyo Institute of Technology in 2014 with a PhD degree. His work for PhD, the title of the work is Study on Development of Zeolite Catalysts for Conversions of Sugars into Useful Chemicals. He also received some awards. The last in May 2023, he got the award from the Japan Petroleum Institute for encouragement of research and development. And his specialty is in the catalytic chemistry and in organic material synthesis. Otomo Sensei, time is yours, maybe around 30 minutes or 40 minutes.
Sorry, 10 minutes?
40 minutes.
40 minutes.
Yes.
Yeah, okay. Thank you for kind introduction, Lina. So, first, I'd like to thank. No, I have. Okay, yeah, but I want this one. Yeah. Okay, first, I'd like to show the big gratitude, Lina. Special thanks. Thank you. So, I'm so happy to be here with you to share my research topics. So, today's my talk is on. You can see the green line. Yes. Okay. You can see. Can you see green light? No. Okay, okay. No problem. today's my talk is on the titanium suboxide material. So maybe almost all of you know, don't know this material, but so I can show you the introduction, the titanium suboxide materials. Can you? Yeah. Okay. Yeah. I can skip. Yeah. Yes. Okay. Yeah. So this figure shows the first diagram. Do you know the first diagram? First diagram. So of 3D transition metal species in the acidic solution. Of course, we know the transition metal species can take the variety of the oxidation state. So you can see the variety of oxidation state and oxidation transition metal and oxidation state. So transition metal species shows the diverse reactivity, chemical reactivity, depending on the chemical oxidation state. So you can know, so of course we know this point because we studied in the high school or bachelor course. So for example, the permanganate species has a strong oxidizing activity, but so mangan 2 plus, Mn2 plus species does not have such oxidation ability. So this difference is due to the oxidation state of mangan. So this is the dissolved species in the acidic solution. But next question is how about the metal oxide? The answer is yes. The transition metal can also take the variety of the oxidation state in the form of the metal oxide. As you can see here, the normalized free energy of the early transition metal oxide, titanium, niobium, vanadium, and so on. So among these metal oxide in different oxidation state, the most stable one is the highest oxidation number. We call it group oxidation number. So like the TiO2, Lb2O5, V2O5, something like that. Okay, yeah. Yeah, so we usually use the catalyst material, these materials as catalyst materials, TiO2, Lb2O5, and V2O5, and so on. So we have much knowledge on these materials, yes, and we have the synthesis method to sort of finely tuning the properties of these materials. But how about the metastable metal oxide? You can see the variety of the oxidation state of these metals, of course, including the metastable metal oxide. But we don't know the properties or synthesis method of metastable metal oxide. So this is the motivation of this work. So the metastable oxidation state, that is divided to 2 different types. Yes. If the most stable oxidation state of a particular metal is N plus now, the metastable oxidation state is one is a higher oxidation state, and the other is a lower oxidation state. If the most stable balance is N plus, the high oxidation state is N plus 1 plus, N plus 2 plus, or lower oxidation state is N minus 1 plus, N minus 2 plus. Okay? For the lower oxidation state, so we studied the titanium suboxide material. So this is today's topic. And also, the high oxidation materials, we also studied the high valence of Fe perovskite, iron perovskite materials. Of course, you know the iron, the most stable valence of iron is Fe2 plus and Fe3 plus. But in the perovskite structure, iron can also take 4 plus or 5 plus state. So these very high oxidation state can show very unique properties, such as catalytic properties. Okay, so today's I will focus on the left side. So here you can compare the titanium oxide, TiO2, and titanium suboxide. You can see the TiO2, the left side, the white powder, And the TiO2 has a rutile or another structure. The most stable structure is rutile. Of course, the most stable, of course, TiO2 consists of the most stable T5-4 plus. So this is a group oxidation number of titanium. But on the right side, you can see the appearance of titanium suboxide materials. So this picture shows the appearance of Ti2O3, typical titanium suboxide materials. So this material has corundum structure, completely different structure from TiO2. And so titanium suboxide material has the general composition of TiNO2N-1. Yes. So from this difference, we can say that TiO2 and the titanium suboxide material has different structure and has different compositions. So TiO2, we frequently use the catalyst, use the TiO2 as catalyst support, and photocatalyst. But there is very limited number of the titanium suboxide materials for catalyst because the synthesis of titanium suboxide is very difficult. Okay, so I will explain the formation mechanism for the titanium suboxide materials. So this is the titanium rutile structure. And you can see here the chain-like structure. So from this structure, in this structure, you can see this structure. So the edge-sharing Ti2 species, edge-sharing titanium octahedron species. So this is a very typical structure for the rutile structure in the TiO2. If the one oxygen atom removed from this structure, like this one, so neighboring oxygen newly coordinated to the unsaturated titanium sites, like tipped down, and to form the new structure, like the right one. So you can see the center of this structure, the triangle face, triangle the plane. So this is a face sharing structure. This is a very typical structure for the titanium suboxide materials. So if we remove one oxygen from every n titanium sites, so repeating this manner forms the new titanium suboxide materials. If n equals 4, we obtained Ti4O7. Okay, that means that this phase sharing structure appears in every 4 titanium sites. Okay, so generally we can say the titanium suboxide material is synthesized by the reduction of TiO2 with some reductants, removing oxygen from TiO2. And there is some synthesis method, conventional synthesis method, to synthesize the titanium suboxide materials. The difference is the reductant, hydrogen, carbon, metal, and metal hydride. But all of these, the reductant requires very high temperature, like 1,000 degrees C. And at high temperature, particle growth occurs severely, and we obtain only very large particle size. So this is a disadvantage for the catalyst, especially solid catalyst materials. And the metal hydride. So this is a very reactive reductant and can reduce the TiO2 at low temperature, below 500 degrees C. But there is another problem. That is a contamination by the calcium species. So calcium, if we use calcium hydride, after the synthesis, calcium oxide was formed on the titanium suboxide surface. So that means the contamination by the calcium element. So these two problems should be solved by the development of the new synthesis method. Okay, so our study has 2 goals. One is a synthesis of titanium suboxide, fine particles, small particles without contamination. And next goal is the application of titanium suboxide as catalyst material. Okay, we developed a new synthesis method using TiH2. So one of the metal hydride about the titanium species, titanium hydride, as a reductant. So titanium hydride is also very reactive and can reduce titanium oxide TiO2 below 700 degrees C, and we can obtain the nanometer-sized fine particles. And the important point is that we use only titanium compounds, titanium oxide and titanium hydride. So theoretically, there is no possibility of the contamination by foreign element. So this slide shows a procedure for the synthesis of titanium suboxide material using TiH2. Very simple. The mixture of TiH2 and TiO2 was added to the glass tube and heated under vacuum at 670 degrees C typically for 24 hours. So TiH2 acted as reductant for TiO2, but TiH2 itself was also transformed titanium suboxide material. So there is no possibility for contamination or for impurity phase other than titanium species. So there is no need for the photosynthesis treatment, photosynthesis purification. So as it is synthesized, we can use it. So this is also a good point. Okay, left side you can see the X-ray patterns of the series of the titanium suboxide materials we synthesized. TI8, O15, TI47, TI305, TI203. So we can control these crystal phase simply by changing the amount of TiH2, the amount of reductant. And the right side you can see the SEM images, so scanning electron microscope images of synthesized and conventional TI203. The synthesized one shows very small particle. The particle size is 50 to 100 nanometer, and the surface area was 21 square meter per gram. But a conventional one shows very large, rocky particles, and surface area was very, very small. So, as you see, we obtain the TI203 or other titanium suboxide materials. So the next step is the catalytic application of materials. So hereafter we focus on TI203. Okay. So another good point, another advantage of this synthesis method is the morphology control. If we use the rod-like TiO2, we can obtain rod-like TI203. If we use the large particle size of TiO2, we can obtain large particle size TI203. From small particles TiO2, we obtain small TI203 particles. So this is also the advantage of our synthesis method. Okay, this image shows the reaction mechanism for the formation of titanium suboxide. So reductant of TiH2 spontaneously decomposes at a high temperature like 500 degrees C to metallic titanium and hydrogen. So the real reductant for TiO2 is metallic titanium. And so such metallic titanium species can cover the TiO2 particle from the outside of the particle. And the reduction progress to the inside or core of the TiO2 particle with retaining the morphology. So we can obtain the TI203 large particle, large spheres, and small spheres. Okay, the next let's move on to the catalytic application of TI203. First, we compare the catalytic performance of TI203 with TiO2 materials in the reaction of the fluoride with 2-propanol. There is two possible reaction ways one is acetylation reaction, and another is transfer hydrogenation reaction. So acetylation gives, of course, acetal with H2O, and transfer hydrogen reaction gives furfuryl alcohol with acetone. The right side, you can see Ti2O3 shows very high selectivity for acetylation reaction, blue. And the activity of the Ti2O3 was higher than zeolite beta and niobium oxide. So typical solid acid catalyst. Interestingly, TiO2 showed the opposite selectivity, product selectivity. So TiO2 only promoted the transfer hydrogenation reaction. So from these results, we can say the catalytic properties of Ti2O3 and TiO2 completely differs depending on the oxidation state of titanium. So it is generally regarded, the acetylation reaction is regarded as solid acid catalyzed reaction. So to confirm this point, we added very small amount of base to the reaction solution of furfural with ethanol. So this, the left side, the figure shows the acetal yield by adding in the addition. So the change of the acetal yield by the addition of base molecules. And you can see the basicity of these molecules in the percentage. So the acetal yield was decreased as the basicity of the additive increased. For example, finally the diethylamine almost completely stopped the reaction. And we also conducted some characterization technique and calculated the number of acid sites on Ti2O3 was 40 micromole per gram. So using this number of acid sites, we calculated the turnover number frequency, TON. So turnover number frequency is the number of reaction occurs on the one acid site or one active site of the catalyst. So the Ti2O3 shows very high, order of magnitude higher activity than other catalysts. So that means the Ti2O3 has very high activity. So the high selectivity is also shown in the acetylation reaction of HMF. For this reaction, Ti2O3 also shows very high selectivity for acetylation reaction. So from HMF, 5-hydroxymethyl furfural, so in addition to the acetylation reaction, another side reaction also occurs, esterification or decomposition reaction. So it is, these reactions are shown in yellow and blue. So both the reaction, acetylation and esterification reaction occurs, the product is green. So you can see the Ti2O3 shows only red bar. That means high selectivity, high chemoselectivity of Ti2O3 for acetylation reaction. TiO2 and NB2O5 shows poor activity, and other catalysts, zeolite beta, amber 15, that is acidic ion exchange resin and toxic acid. So for these catalysts, the product wide, these catalysts shows the very wide product distribution, not selectivity, not selective for this reaction. So from these results, we can say that Ti2O3 is highly active and highly selective catalyst for acetylation reaction. Okay, next we used Ti2O3 materials as catalyst support. So there is some significant effect of catalyst support on the catalysis of a supported catalyst. So catalyst support can increase the dispersion in the surface area of active species and changes the electronic state of reactivity of active species. And also there is synergetic catalysis between the active species and the catalyst support. We found a very unique catalyst support effect of Ti2O3, that is redox interaction between active species and Ti2O3. So Ti2O3 has oxidizing ability, reducing ability, and Ti2O3 can reduce the active species and keep the active species in the low oxidation state. But as a counterpart, Ti2O3 was partly oxidized. Okay, we chose the cobalt oxide material as active species in this study. So the cobalt oxide species was prepared as like this by the precipitation deposition method. And finally, the catalyst was heated in helium flow at 300 degrees C. We obtained 10 well% cobalt oxide, supported cobalt oxide materials. And we use the Ti2O3 and TiO2 alumina silica inactive carbon as catalyst support. So after the synthesis, the general catalyst support shows the X-ray pattern of cobalt oxide as CO3O4. The CO3O4 is a mixed valence cobalt oxide materials consisting of CO3 plus and CO2 plus. But in the case of Ti2O3, cobalt oxide was supported in the form of COO. COO consists of only CO2 plus. So that means cobalt species was reduced in the synthesis in the preparation procedure. So you can see the right side. For general catalyst support, CO3O4 was supported, and after the heating in helium, the CO3O4, the structure was retained. But Ti2O3, for the case of the Ti2O3, CO3O4 was reduced to COO by Ti2O3. And the near surface of Ti2O3, it was partly oxidized. So the reductive effect of the Ti2O3 support was also effective in the reductive environment. So the left side, you can see the X-ray patterns of the samples after treatment with hydrogen at 250 degrees C. So for the general catalyst support, the cobalt species was reduced to COO, so yellow triangle. But in the case of the Ti2O3, cobalt species was reduced further to metallic species metallic cobalt. So the Ti2O3 has reductive effect, but this reductive effect was also effective in the hydrogen atmosphere and facilitated reduction of cobalt oxide COO to metallic cobalt species. So we applied these cobalt oxide materials for the HDO reaction, hydrodeoxygenation reaction of anisole. So HDO reaction from anisole produces benzene as desired product. But in the hydrogen environment, possible side reactions occurs, such as hydrogenation to cyclohexene, hydrogenation to methoxycyclohexene. And also and hydrogenolysis. So also the anisole species, the causes the acid catalyzed reaction like methylation reaction, methyl transfer reaction to alkyl benzene. So we use these cobalt oxide catalyst materials for vapor phase HDO reaction in the vapor phase, okay? So this figure shows the reaction results over cobalt oxide, supported cobalt oxide catalysts. So Ti2O3 shows the very high selectivity and the high activity for benzene HDO reaction. So other catalysts shows lower activity or lower selectivity. So generally, cobalt oxide catalyst was much better than molybdenum oxide. So in the reductive environment, cobalt species were reduced metallic cobalt species, and such metallic cobalt species can activate hydrogen to form the adsorbed hydrogen, and such adsorbed hydrogen is reactive species for HDO reaction. Okay, Ti2O3 catalyst support also effective for extending the catalyst life. As you can see here, so here we compare the catalyst life and the catalyst stability between Ti2O3 and TiO2 catalyst support. So for the case of TiO2 support, the conversion of anisole and the yield of benzene suddenly dropped after the start of the reaction, but Ti2O3 support shows much better stability and longer catalyst life. So after the reaction, we conducted the XPS analysis of the spent catalyst, and we found that the oxidation of the cobalt species during the reaction is the cause of the deactivation. And Ti2O3 catalyst support can facilitate the reduction and regeneration of reduced cobalt species. So that is why the Ti supported on cobalt species supported on Ti2O3 shows longer catalyst life. Yes, okay, I will skip this image. Okay, let me summarize this study. So we developed a new synthesis method using TiH2 for the formation of titanium suboxide materials. By using this method, we can obtain the series of titanium suboxide materials with the crystal phases controlled. And Ti2O3 material acted as solid acid catalyst and showed high activity and high selectivity for acidization reaction. And Ti2O3 catalyst support facilitated the reduction of cobalt species and enhanced the activity of cobalt species for the HDO reaction. And the last message from me is the potential of titanium suboxide material is, as catalyst material, is to expand faster, I think. Okay, I'd like to thank all of our group members, funding agency, and all of you for kind attention. Thank you.
Thank you so much, Otomo Sensei, for your nice presentation. So maybe Otomo Sensei and Kamiya Sensei can sit in front, and let's open discussion. So for Kamiya Sensei already presented the reductions of nitrate in water, and just now Otomo Sensei presented of the synthesis of the metastable oxide. In this case is titanium suboxides. So questions, boleh pakai bahasa Indonesia, nanti saya terjemahkan, boleh. Okay, one questions, do you have your mic now? Okay.
Thank you so much, Kamiya Sensei and Otomo Sensei. I have question for both of you. Maybe start from Kamiya Sensei first. So the selectivity and the formation of ammonia is changing due to the condition of the reaction. That's right, Sensei, right? And I noticed on the slide, the condition changing about the pressure, right? So the pressure of hydrogen from 0.025 into 0.05, it's changing. And then the formation of ammonia also changing. So can you please explain why the pressure can affect the formation of ammonia? That's the first question. And then for the second question for Kamiya Sensei also, about the last material, you said it's reusable for at least 5 times, right? So each reaction using the catalyst, it reduces the activity of the catalyst. So can you explain why there is a degradation of the function of the catalyst? And is there any way to prevent the degradation of the catalyst activity itself? That's for Kamiya Sensei. Yeah. And also for Otomo Sensei, I got one question. In the last slides, you said that the TO2O3 catalyst, it has a longer lifetime of catalyst, right? So I assume it's also reusable. right, to use it again and again. Please, maybe you can clarify, is it reusable, the catalyst itself, and maybe how many times can we do the reuse of the catalyst itself? Thank you.
Okay, thank you, Rinanda, for the questions.
Okay, thank you very much, Denanda. So I'm sorry that I cannot catch your second question. So later, please explain. But before that, I will answer your first question. So the good point. So you studied in my laboratory for 3 months. So you have the good sense on catalytic chemistry. Okay. So as I explained in my talk, that the concentration of hydrogen atom on the palladium side can determine which product is formed. If the concentration of hydrogen on the surface is low, instead the concentration of nitrogen atom on the surface is high, the dinitrogen molecule tend to be formed. On the other hand, if the hydrogen concentration on the surface is high, ammonia is formed. So the concentration of hydrogen on the catalyst surface is determined by the partial pressure of hydrogen. So if the partial pressure of the hydrogen is high, which means the hydrogen is pressed on the surface, so the surface concentration of hydrogen is high. So under such conditions, the ammonia tend to be formed. So to prevent such conditions, we decrease the partial pressure of hydrogen. So under these conditions, the surface hydrogen concentration may be moderate. We cannot direct evidence, but the moderate hydrogen concentration. So as a result, the ammonia formation was decreased. Instead, the nitrogen formation is preferred under such condition. So sorry, the second question.
The second question about the reusable catalyst, Sensei.
Reusable.
Yes, on the slide, you said at least we can use it 5 times.
Yes.
Yeah, so is there any preventive way so we can use it maybe more than 5 times?
Okay. So your second question is on the second part of my research. So I'm sorry, so we have not checked for example, the content of the active metal particles embedded in the material after the 5 reuses. But according to the performances, so performances are almost stable for 5 consecutive reuses, so which imply the content and the structure of the metal particles embedded in the anion exchange regime did not change by repeated use. But we have to check for example, the particle size distribution by TEM and the content of the gold by ICP-AES, I think. So very good point. Thank you very much.
Thank you for the question, Denanda. So you asking me the regeneration of the catalyst. So cobalt species supported on the Ti2O3 support. Yes, so cobalt oxide supported on the Ti2O3 shows much better stability and the longer catalyst life. But yeah, actually it is deactivated slowly. But we also conducted the regeneration treatment of the catalyst. So we conducted hydrogen treatment of the catalyst again, and we found the almost complete regeneration of the catalyst activity as the initial state of the catalyst reaction. So we can say, yeah, our catalyst is very easily regenerated for HDO reaction. Thank you.
Okay, thank you so much. Any other questions? Yes. You can say your name and your faculty also.
Yes. Thank you for the time. My name is Mazlan. I'm from environmental science, but my master in chemistry. Thank you for the information about how to use heterogeneous catalyst for wastewater treatment. But maybe I will ask in Bahasa Indonesia because my English not very good. I have 3 questions. The first one, yang pertama yaitu terkait dengan biologi treatment, biologi method and chemist method. Kelebihan dan kekurangan metode ini dalam melakukan treatment terkait dengan air. Mungkin gitu ya Bu. Pertanyaan saya, apa kelebihan dan kekurangan menurut beliau terkait dengan penggunaan biologi dan kimia, khususnya di katalis heterogen. Kenapa? Karena dominan di tempat kita itu masih menggunakan biologi. Kita tidak menggunakan heterogeneous katalis heterogen dalam mentreatment air.
Kalau begitu saya jawab dulu ya.
Yeah.
Karena beliau adalah kemis, maka beliau tidak akan tidak akan membahas yang biologi. Begitu. Jadi nanti kalau misalnya saya akan sampaikan keuntungan dari treatment secara kimia begitu ya.
Tadi kan beliau membandingkan antara resin
betul.
dengan
kalau tadi beliau kan mengatakan bahwa NO3 itu karakteristiknya adalah sebagai oksidan, kemudian sebagai ion exchange dan sebagai nutrien. Nah, untuk menghilangkan menghilangkan NO3 sebagai nutrien seharusnya menggunakan biologi, ya treatmentnya biologi. Nah, beliau hanya menyampaikan yang 2 sebagai menggunakan reduksi sebagai oksidan, kemudian yang satunya sebagai ion exchange menggunakan resin. Oke, boleh. Oke. So the first question is ya.
Terima kasih.
Yang kedua, for the second question, terkait dengan penggunaan CU, apakah itu safe untuk lingkungan, dan karena sekarang kita rata-rata bagaimana mengabsorb CU di limbah. Itu yang kedua. Kemudian yang ketiga, saya punya case, Bu. Yang ketiga case-nya ini kalau di Karanganyar, saya sering terjun ke sana, mereka itu punya masalah kandungan Fe yang tinggi. Kalau menggunakan resin, menggunakan kimia, paling 1 hari udah harus ganti. Apakah mungkin ada solusi dari beliau terkait dengan isu ini? Terima kasih, mohon maaf.
Okay, so his second question is, when you use copper as your metal as your active sites, will it become a problem? For example, is it toxic? So for the environmental point of view, what is your opinion about this?
Okay.
Yeah.
So it's a very good point. When the heterogeneous catalyst is used for water purification, of course, the copper is some kind of the toxic properties. So we have to completely prevent copper from dissolution. Of course, we check how much amount of the copper was dissolved during the reaction. So according to the result taken by ICP AES, no copper was detected. But so I think if some conditions of groundwater is changed, so which potentially make the copper dissolution. So we have to check the dissolution of the copper for the target groundwater, polluted groundwater.
Okay, do you sudah cukup? Okay. So the third question is, so the last question is, so he has some cases. So he comes from one of the nearest town from Solo, it's Karanganyar. So if we go maybe east part, then we will arrive in Karanganyar. So he said that in Karanganyar, the water is polluted by iron. So
Iron.
yeah, iron. So he said that if you use resin, then only one day it will be, useful. Then the next day he has to change the resin. So do you have any idea on how to prevent this kind of problems not to occur again?
Okay, so you want to remove the ion by using the ion exchange technology,
Yes.
right?
Yes.
But so firstly, of course, basically the iron is present as a cation, so iron 2 plus and iron 3 plus. So you have to use the cation exchange and cation exchange resin to remove the cationic iron species. But problem is the selectivity for iron 2 plus and iron 3 plus, because the real groundwater, polluted groundwater, contains the various kind of the cationic species other than the iron 2 plus and iron 3 plus. So you have to choose the appropriate ion exchange resin selective for iron 2 plus and iron 3 plus. But I'm sorry, so I'm not so familiar with the cation exchange resin, so I cannot give you a good concrete idea. But selectivity is very, very important parameter if you want to apply the ion exchange technology for groundwater purification.
Thank you for the information.
Thank you. Okay, the next is.
Okay, thank you for the time. I want to ask, my name is Nandi Samu from Chemistry Department. I have 3 questions, okay. The first one is for Professor Kamiya Sensei. I want to ask about the random assortment of palladium and copper composition in the active site of the catalyst. First of all, in your presentation, the oxygen is absorbed in the copper side and the nitrogen is on the palladium side. In my research group, we are doing catalytic for oxygen reduction. And when oxygen reduction usually absorbed within the catalyst. And palladium usually is good for oxygen absorption too. So what I want to ask is it palladium and copper combination really makes the difference who is the one at absorbed with? Are you understand my question?
I'm sorry, so I cannot catch your question,
Okay.
but you are now asking about the copper palladium system and
what I want to ask is the selectivity. Is it the oxygen will absorb in the copper side or the nitrogen will absorb in the copper side? Because many metals have different absorption selectivity, and palladium usually more selective, more absorbed than other transition metal. So I want to ask, is it really selective to combine the copper and the palladium? Sorry for my complicated
okay. This is just you want to receive a comment from.
No.
Okay. But anyway, the copper is an element to be easily oxidized by some oxidizing reagent, including the dioxygen and nitrate. So in my case, the reaction conditions is reducible condition, because the hydrogen is present in the gas phase. So we don't need to think about the presence of oxygen. But in your case, the oxygen and the other oxidant are simultaneously present in the reaction system. So if so, I think firstly you have to think about is the concentration and the partial pressure of each oxidant. So if the copper, I'm not sure, but if the copper is selective to the other oxidant than O2 molecule, I think concentration of oxygen is very, very high. So maybe the oxygen tend to react with the copper side. So of course, the selection of the element is very, very important to develop the highly selective material for dioxygen molecule. But the reaction conditions, especially the partial pressure and the concentration of oxygen, should be controlled as much as possible. Of course, so if the electronic state of the copper can be changed by the addition of the second and third element, I think the material may show the high selectivity to oxidant other than O2. So please try as much as possible.
Yes. Okay, thank you for the answer. I want to ask again to Mr. Otomo Sensei. So what I want to ask is about the metastable of the metals. So in your research, you are using titanium oxide. What I want to ask is, are there any other abundance transition metal that can be used as the metastable catalyst? Because titanium oxide is usually a heavy metal and precious metal, and we want to use more abundance metal to make catalyst. So if there are any example of other metastable metal catalyst. Okay, thank you.
Okay, thank you for the question. So honestly, I can say, so transition metal can take the variety of oxidation state. Yeah, but other species cannot take the multiple oxidation state. So we can synthesize the variety of metastable metal oxide using transition metal oxide. Of course, transition metal oxide is a part of the heavy metal, so we can only use the transition metal for the metastable oxide. But if we focus on the transition metal, we can synthesize the very, very wide variety of the metastable metal oxide. Yeah. In this study, I focus on the titanium metastable oxide, but also our group studies catalysis over niobium metastable oxide species. And so metastable niobium oxide shows different properties from the Ti2O3 and the other titanium suboxide materials, and also from niobium, most stable niobium oxide, Nb2O5. Yes, and you can find so many papers on the metastable molybdenum oxide. Yes, because molybdenum oxide is very easily reduced into the metastable oxidation state, MO4+, MO3+, MO2+. So you can find many papers and you can refer to that. Okay. Thank you.
Thank you for the answer. I agree.
Any other questions? Okay.
Thank you for the time. I'm Anissa. I want to ask to Professor Kamiya about the catalyst. The first one, the chemical reduction. The chemical reduction one. So the most effective, you say, is the combination of copper and palladium. So I want to ask if you have tried the other composition without the noble metals, so like copper with iron or so. And then for the anion resin, I noticed that you use different metal that you use in the chemical reduction, and why so? Because the selectivity of the copper and palladium is like very high, 100%, and why you don't just like incorporate that into the resin? Thank you.
Okay. It's a good question, but maybe my explanation during my presentation, my lecture is not so understandable for you. So the role of copper and the palladium are completely different. The role of copper is the stoichiometric reduction of nitrate, okay, into the nitrite. As a result, the copper is oxidized into the copper 2+. And then the copper oxidized copper species must be reduced by hydrogen activated on palladium. So copper is indispensable to proceed the nitrate reduction. So on the other hand, the role of palladium, one of the role of the palladium is activation of H2 into the atomic hydrogen on the palladium site. So palladium is a precious metal. So most precious metal has such kind of the property to activate hydrogen to metallic atomic hydrogen. So for example, the platinum and the iridium are also applicable as a precious metal element for this catalyst. But the point is the nitrite reduction. So nitrite also must be reacted on palladium site. Unfortunately, for example, the iridium and other transition metal only showed the catalytic activity for nitrite reduction. But I'm sorry, I'm not so the concrete reason, but the palladium and the platinum are the good precious metal for the nitrite reduction, NO2- reduction. So that is the reason for us to must be used the palladium and copper systems.
Oh, the second question not yet answered. So why don't you use the copper palladium on your resin?
Copper palladium resin. Okay. So reaction system is completely different between the supported copper palladium catalyst and the copper palladium resin system. So in case of the copper palladium system, the catalyst is put in polluted water. So which means the reaction takes place in water. On the other hand, the second system, after the removal of nitrate by the reaction of the by ion exchange reaction, the resin taken out and then put in a flow reactor. And then the temperature increase up to 80 degrees Celsius. So the reaction is not performed in water, rather the gas phase reaction. So of course, the copper palladium anion exchange resin showed the activity for this reaction. But the two elements, the combination of two elements makes the catalyst design complex. So ideally, the single element is better. Okay? Single element is better. So in case of the metal anion exchange resin, the reaction temperature is a little bit higher than the reaction in because higher. So the two elements are unnecessary. Only one element, for example, the gold, ruthenium, platinum, this single metal catalyst showed the activity for nitrate reduction in the resin. So we don't need to use the two elements in the second system.
I think it's enough because this is Friday. So some of the gentlemen needs to go to the mosque for the praying time. And thank you, Kamiya Sensei and Otomo Sensei, for your nice presentations and for your clear response for our questions. So please give a big applause to both of them. And the first session is closed, but the second session will be start again here at 1 p.m. So please come again at 1. And we still have 2 more presentations from Onoda Sensei and from Nakajima Sensei. They will have different topics. Onoda Sensei maybe focus on the biosensor, and Nakajima Sensei will focus on the biomass conversion. So it's also going to be really insightful and really useful presentation. So please come again at 1 o'clock in the same place. Thank you so much. See you again.
Cek cek 1 2. Cek cek. Cek cek cek. Cek cek. Cek cek. Cek cek cek. Cek cek cek.
Good afternoon, ladies and gentlemen. Selamat siang adik-adik ya. Kita akan menyaksikan lagi research talk ya. We will have research talk here, the second section, with two speaker. He is Prof. Akira Onoda and Prof. Kiyotaka Nakajima. And the first speaker will be Prof. Akira Onoda. Before he deliver the speech, let me to read his curriculum vitae. Prof. Akira Onoda, he is a professor in the section of Environmental Material Science, Faculty of Environmental Earth Science, Hokkaido University, Japan. He received his PhD in the macromolecular science with the title of his dissertation is Metal Oxygen Bond Regulation by Rearrangement of Hydrogen Bonding Networks. He was also associate professor at the Department of Applied Chemistry, Graduate School of Engineering, Osaka University. And he received some award here from he received some award from Chancellor's Incentive Award from Osaka University, and he was also the first Incentive Award of Japan Association of Chemical Innovation. About his research field, yeah. He works on bio-inorganic chemistry. This is one lecture that I have also in this university. I teach this lecture, bio-inorganic chemistry, and about metalloprotein engineering, biotechnology, material science, and chemical biology. Now it's your time, Prof. Akira, to deliver the speech. We give applause first, yeah, to Prof. Akira.
Thank you very much for a very kind introduction for Chairman. And then also I would like to Lina to this great opportunity to share our work and also Kamiya to take me this great journey to Indonesia. So today I would like to share my the work about the biohybrid catalysts harboring synthetic metal complexes within a viral protein. And I think this would be a quite new topic I would like to share from the basic. So I'm chemist and also biochemist. I really enjoy the tempeh in this trip. It's a fermented bean, which I learned this week that this was done by this bacteria, and then this was made for banana leaves. So in Japan, we have a similar type of fermented bean, which we use from rice straw. It's really sticky and smells bad. All right. So I think I would say that tempeh would be the better food. But if you have a chance, please try, right? Okay, so as outline, I would like mainly share about our topic on biohybrid catalysts. And if we have some time, I would like to share. I would like to introduce other work on because we are very working on the chemical modification of proteins. So we applied this to the biomaterials or the surface modifications. As an extension of this, I would like, if we have a time, I will quickly show about some new technology for the chemical modification, which is developed in our group. So, process engineering. We heavily depend on both for the biology and chemistry for both catalysts. In the morning, we have learned beautiful heterogeneous catalysts can convert a lot of important transformations. But as we see in the natto or fermented food, both of the biocatalysis and chemical catalysis is really, essential for to maintain our society. And why the biocatalysis is attractive? Because they can evolve, right? They can amplify by themselves. And if you can modulate some mutations to the proteins, you can easily generate a new catalyst, right? So that's why these biocatalysts is used for a lot of conversion in the chemical reaction, even in pharmaceutical products. Okay, so the question, why we have to marry this chemical catalysis and biocatalysis? Of course, advantage of biocatalysis lies in evolution. We can evolve the enzymes, and this was already done, and which was awarded a Nobel laureate work in 2018 by the Professor Arnold. And nowadays, the combination of the chemical catalysis and biocatalysis is done by the tandem, as a tandem catalysis, right? Then you can shorten the process using a chemical process. And what I'm working is artificial metal enzyme, which is not in a practical phase. But if you combine these two chemical and biocatalysis, we will have a non-natural, really remarkable reactions. So, I would like to introduce some, what is artificial metal enzyme, and in other words, biohybrid catalyst. So the catalyst in chemistry, so you can use this for a variety of unnatural reactions. And basically the chemical catalyst is really highly active. 40 minutes, right? So, and that means the reaction has a broad surface and robust, and then the reactivity or selectivity can be modulated by the ligand design, right? And if you focusing on the biology, the biocatalysis generally works in mild conditions, right? Efficient, the substrate specific, and then importantly, the residual and enantioselective selective. And these can be done by modulation, second sphere of the coordination site, of the active site. So the idea is how we can implement the advantage of these two. That's the basic concept of artificial metal enzymes. So going back to 1978, the Professor George in MIT, he first showed that enantioselective selective reaction using the protein scaffold, right? This is it's a 41% EE. It's not that high, but that's a conceptually big milestone in this field. So since then, over 30 or more than 30 years later, there's many approaches to generate or construct artificial enzyme have been done. So, so basically, how we can anchor the metal complex, right? So here I show that. I mean, this is a basic concept. So you can link the artificial metals by non-covalent coordinations or supramolecular interactions to deliver into the protein scaffold, or you can link to covalent specifically, or other recent attractive approach is non-canonical amino acid, right? You can generate non-canonical, you can generate amino ligand into the peptide side chain, and then put in, incorporate the proteins. So I can show a very brief example for what kind of example in artificial metal enzyme in general. For myoglobin, very simple, quite famous protein that has a cofactor, iron cofactor, heme B in the pocket, right? So how we can engineer this? One particular example I pick up just from the review. You can modify the cofactors, the shape of the cofactors, or slightly modified in the middle, or the quite different. This is a saline, but it's flat, planar, and then hydrophobic. So this can be incorporated in the protein. Even chemical and the ligand structure is quite different. So here's the one crystal structure. It actually deposits in the pocket, right? On the right is the native protein, left is the artificial protein, which has a different cofactors. Or here I show the other very successful example using a supermodel anchoring. Here you see the biodine on the left with it's hard, but the biodine small molecule linker is linked with the metal complex on the right side, right? So then the protein streptavidin binds specifically to the biodine entity on the left side of the thiol-containing ring. So the metal complex on the right side is incorporated specifically to the protein scaffold. Like this. So here's a protein scaffold, and then because of the biodine entity on the left side of the linker, can have a very strong affinity. So the metal complex is, easily delivered to the protein scaffold. So this is one example. For here, I showed trademark work reported in Professor Ward's group. So he showed this rhodium complex embedded in a protein catalyzed these reactions. Or if you put the iridium myoglobin on the right bottom, so performs the cycloaddition cyclocarbene insertion reaction using the protein myoglobin is scaffold, which is non-natural, unique reactions. Okay, here's I can show some other very examples. Here, in this slide, I show some which is developed in my group. So we've the quite rigid and protein scaffold, and they put the variety of metal complexes, rhodium, ruthenium, or and we did try the variety of reactions. So I show a couple of examples what we have done in this over 10 years. So when this was done, I belonged to the Osaka University in 2012 to 14. So the Kazuki tried tethering the rhodium complex into the protein scaffold, and this catalyst generates the cis phenylacetylene. But if you put into this rhodium complex into the protein, we have a trans polymer, which is a different stereo selectivity. So I show a little bit more in detail of the system. So, the phenylacetylene can be polymerized by the rhodium, generating the cis polyphenylacetylene. Of course, if you use the tungsten hexachloride, we get the trans polymer. And so how we can control this? This is an interesting question. And with one example using the protein, using the ferritin cage, this controls the length of the polymer. But at that time, there's any report on controlling this stereochemistry of this polymer. So what we have done, we designed the rhodium complex, which did the malate imide group on the left side. So the rhodium imide quite catalytically active, and we use a CP cyclopentadienyl ligand and malate imide entity to link specifically to the cysteine residue. I can show what this goes on, and we selected the nitro-binding beta viral protein, as you see on the right side, and this is quite a robust structure because this has a 10-stranded beta viral and contains a hydrophobic cavity. So here's a structure of nitro binding. So inherently, this contains the native heme inside, and then we remove the heme and to incorporate the synthetic non-natural cofactors, right? And so we screened all positions of the surrounding cavities to incorporate the metal complexes. So the cysteine is to link the malate imide to deliver the rhodium complex. So we screened all positions, and we find out the 96 position is quite suitable for our purpose. So as you see here, we prepare the nitro binding with this 96 C mutant, and we make a covalent link with the specific position system. So we characterize mass spec. It is actually one-to-one covalent linked complex. And then we also get the crystal of this complex. As you see here, in the middle, we actually clearly see the CP star rhodium complex is linked and embedded in the hydrophobic cavity. If you get closer, this cyclopentadienyl entity is surrounded by the hydrophobic amino acid. And importantly, this rhodium center is quite directed to upward to the protein scaffold. So this is suitable for the reaction with the phenylacetylene. So then we started the screening, tested the reaction with the phenylacetylene, and in the emulsion condition, we have this cis and trans polymer. So we analyzed by protein NMR. With the reference, we tested some other myoglobin protein, which link the rhodium on the surface, right, to know the effect of the cavity. So here's the results. So the rhodium complex generates the cis-rich polymer, and the myoglobin in the entry 2 give the same, the cis-rich polymers. But when you put in nitro-binding protein, we have, half-trans ratio of the polymer. So the protein cavity do something, right? So what happens, so here's a possible scheme. I don't go in detail for this, but the protein cavity will perturbs isomerization during the polymerization step, because here's the model of the protein scaffold plus oligomers are linked to the rhodium site. It's really congested, right? Too crowded. That disturbs the polymerization in cis-rich polymer. So, here's the summarized point of the effect of the protein scaffold. So the larger cavity will, easily, smoothly isomerize, but the tight linked cavity will restrict the approach of the substrate. So these effect will generate the rich polymers. So now we know the effect. We screen around different types of cavities, so make a larger cavity, smaller cavity with these kind of mutations, and prepare the similar type of the reaction environment. So we choose the nitro-binding protein, which is quite easily crystallized. So we can, most of them are crystallized, and then check the void space of this protein cavity. And so these are the larger ones for the alanine mutations. Also, we make a much smaller cavity with a tryptophan variant on the right bottom. And then we make the same way for that, prepare the link, the rhodium complex, and screen it. And then it turns out that entry 6 and 7, those variants have much higher trans ratio, maximum 82%. So based on these mutations, we can, perturb the regioselect polymerization of phenylacetylene. Okay, I move on to the next topic. So, the advantage of using the protein scaffold lies mutations, right? And then if you accumulate this mutation, the number of the screening much increased. So this is the advantage. We have screened a large number of space. But how you can do this screening system is the biggest point. So we call this directed evolution of the, in this case, biohybrid catalyst. So there's several approaches. So as I introduced, like a supramolecular approach is also effective. There's a couple of examples. But the point is you have a limitation in the protein scaffold, because you have some small molecule that link to the specific protein scaffold. So you cannot change the protein scaffold as you like. So in the middle, non-canonical amino acid. So we can incorporate the non-natural amino acid into the protein scaffold. So anchoring specificity is perfect, but when you try this experiment, so that you use a lot of amino acid, but you can obtain that really tiny amount of the protein, what you want. So this is really the bottleneck of this system. But of course, you can try the variety of proteins. So the covalent modification with cysteine, which I showed in this talk, is of course specificity, anchoring efficiency depends. So it's moderately good, but the advantage is we can apply to this method to any kind of protein, basically, whatever you like. So we stick on this strategy and develop to do the direct evolution using this cysteine-linked approach for the artificial metal enzymes. Okay, for this purpose, we use this CP-star rhodium complex, pentamethyl cyclopentadiene complex, which really often used for the organometallic community, because this CP-star rhodium complex has a 3 vacant open space to accommodate the ligands and substrate, and then it really do the many kind of stage activation reactions. But if you use this CP-star rhodium complex in the cell, in the protein, it's so active, so then the many kinds of ligands, like you see in the lysine, histidine, they coordinate to the rhodium center, which deactivates the activity of this rhodium complex. So we have to solve this problem, right? To solve this problem, we make the one idea to implement the latent activity of rhodium complex. So the story goes like this. So rhodium complex with higher activity is protected by the ligand, and then we conjugate. After the conjugation, we can deprotect and activate the rhodium center by addition of other metals to peel off the ligands, protected ligands. So the second idea we implemented for this to do directed evolution is to find out the easiest reaction probes. So select this cycle addition reaction of the oxime and the acetylene to generate the quinoline product. Shows the fluorescence. So we can screen the product by only the fluorescence. We don't need to measure NMR all the time. Okay, so here's the first part of the screening to find out the latently active rhodium complex. So it should be protected, but it should be protected, but it can be also peeled off, addition of some other metals. So we screen several diethyl ligands, malonyl or diethylcarbamine, and rhodium phosphate, rhodium 5. So these complexes is tested, and then we found out with this rhodium complex 5 shows recovered activity in the addition of silver ion. I don't go into detail on this screening. So, but anyway, we can regenerate the activity of the rhodium complex, addition of the silver complex, start with the CP-star rhodium complex linked with the thiophosphate ligand, right? So here's the rhodium 5, and then we make a rhodium 5 with a maleimide group to link the protein. And as you see here, a CP-star rhodium complex is higher active, and even though after we linked with the protein, nitrobinding protein, I show you in the last part of the talk, also shows the activity in 50%. So it's getting lower, but it's enough activity to start the screening. So now we established the system to link the rhodium complex. So we move on to how we do the actual directed evolution, screening, and then find out the good mutants. So to make a gene library of nitro binding, and then you express them and link with the protein, and then you pick a nice position. So this is, and then you can round and round and round for this screen. So I mean, if you change the 10 mutations, you have trillions of variations. So this is difficult. This is the advantage of the directed evolution. You can screen the wide space, right? But the problem is here again is how you link the cofactor, right? So in the cell culture or lysate, so this is something we have to screen out. And then to screen the large number of a protein in a purified system, you need a large number of resins. So this is a problem. So to overcome this problem, we use the maltose binding protein that binds to the, maltose basically. So we use the resin to bind, we express the target protein as a MVP protein to do this direct evolution. So here's a detail of the flow. So you have a plasmid as a fusion protein of a nitrobinding and MVP protein, and then express it in the E. coli, and then so we made a whole surrounding amino acid, 20 amino acid, to hold different variations. So over 4,000. But it's not a difficult work for this system. So, and then we express and lyse the cell, right? You lyse, and then with the lysate, we can add directly rhodium star complex. So even in this complex mixture, we can link the CP star rhodium complex with the protein, right? So then we purify using a starch agar resin. But here's a problem. Bind the, fusion protein P. So the amylose is expensive. Like this on the left with Lupia. I showed in Lupia. And then I forget to remove the yen mark, but on the right side. So this is too expensive. So the students, Shunsuke, was frustrated. He wanted to screen more and more. So he needed more resin. We need more money. So it's too expensive. That's why he developed the homemade bees, which can pretty easily made by the starch and mixing the starch and agar. So it's very cheap. So he can now ready to screen many plates, many. So now we have a very cheap resin, so we can start roughly 96 web plate, meaning roughly 100 variant in one plate. So we can screen many with this system. And then we also have a fluorescence probe to detect the activity. So we go directly to the plate leader to check the activity and the expression level. So now 4,000 variants of the screening system, so then we know the activity. So here's just an example for just lining up the activity which from the top ranked activity. We know, so it varied, which means this is direct evolution system, right? You mutate at some position, some has a lower activity, some has a higher, right? So we don't know who is the best. But now and then you pick some successful variant, we screen. We test sequencing, we know this K127E. The lysine is converted to the glutamate. Positive charge side chain is changed to negative residue, shows a quite high activity. Okay, so now we set up the system and then we know which variant shows the higher activity. First round, we know this T98 is good, and then we can combine the second round with the L100, K17 is good. We mix this variant. So these three positions nearby the rhodium complex shows much activity. So we go to the fourth round, it was not successful, so but at the end, from the over the 4,000 screening, we know this is the best variant. Okay? So the profile for the activity is like this. So starting from the, normal variant from NB4, we say, change it to the different variant shows, like this, much higher activity. 5 minutes more, right? So I skip this. And okay, so now we have a direct evolution system, and then we can, as I said at the beginning, the advantage of this system is we can change the protein scaffold as you like. So next step, we focus on how we can improve the activity as a next step. So at the beginning of the protein design, we use nitro binding, which is the nicely open space, right? It looks like this. So the rhodium complex is freely accessible for the substrate, right? But within the shallow cavity. So, but it turns out that the affinity might be not enough for the substrate. So the idea now we have is to introduce the cap domain to improve the affinity with the substrate. So then this metal enzyme has a more confined space to do the reactions. How we do that? So we choose the fatty acid binding protein, right? So, the fatty acid binding protein binds the fatty acid. So really tightly, we also have the fatty acid binding protein, and then it has a 10-stranded beta barrel structure, which is quite similar with the nitro binding we have been used. But exceptional thing is they have an additional, like a lid on the barrel, right? So, okay, this will be nice. So we pick up this helix loop, helix domain, and then remove it off, and then put it into our artificial metal enzyme on the nitro binding. So it will accelerate the substrate binding. Let me check the time. Okay, so how we do that? How we do the make a fusion protein? We introduce this helix loop domain in summer of this fusion protein. But as you see here on the left bottom, from the top, this is a view of the top of the nitro binding. It's a barrel, so we have to choose where we link the loop, which loop will be suitable to link this helix loop, helix domain. So we pick up the two parts of the loop between the loop between the strand 3 and 4 or 7 and 8, right? And then, so we put this helix loop domain, which is colored in yellow around. But the next question is, the length would be suitable or not, right? We don't know. So we link the amino acid as a linker, and then several put amino acid linker, and screen produce this variant and then screen with a similar system. So, but if you change the variant, particularly we introduce a large domain, the expression level in E. coli. Sometimes E. coli don't like to produce a lot. So we have to know the concentration of the protein. So we check this by OD280 absorption. And we know the product, kind of yield from the fluorescence for 70 nanometer. With these two parameters, we know the production level of the enzyme and then reaction yield, right? Okay, here's the profile of this the variant. So we use a pick up the similar type of the cycle addition reaction of this oxime and then alkyne. We change a little bit of the methox group in this system to make it more substrate soluble. And then we have the same way as the isoquinoline product can be detected fluorescence for 70 nanometer. And then here's a time course analysis on the left, you see, and here's a nitrobind in the bottom, and we introduce the helix loops domain. It shows much higher activity, right? And then we modify the linker, right? Then we see a little bit AP, FY, and F is the version we introduced the mutations of the linker. It shows much higher activity. Great. So then now we have a better variant. So we finally optimize the interfacial residues between the barrel and the loop region on the right side. So I don't explain the detail, but we do the two round of the selection, and then the final variant, APFY and HD, has a much higher activity. And then we also perform the kinetic analysis, reaction with a different type of, different concentration of substrate. We have two substrate with oxide, alkynes. We do the both, and here I show the one example. And as you see here, on the starting variant with only 26 km. Sorry, the kcat over km in the bar, and then I also show the km. So the km goes starting from 100 to the 26 in the final variant, meaning the much higher affinity with the substrate. Accordance with this much higher increase of overall activity with the kcat over km. So, I mean, from this screening over 4,000 variant and with the combination with the domain fusion, show the much higher activity. We have done this work with Shunsuke is that have done work on this work, and then this was done by collaboration with the group of Schwaneberg in Aachen University. Okay, I think I'm almost done, right? I just go directly to the conclusion. Okay, so the work I showed is mostly done in group member of Hayashi group. Particularly, I thank for the Shunsuke I showed in the slide, and also the funding, which is which I show here. Also, I would like to thank for the current members in Hokkaido University, and thank you for your kind attention.
Thank you, Prof. Akira. Maybe we will continue directly to Prof. Nakajima, and then we can continue with question and discussion after that. Yes, to save the time. Yes. The next speaker will be Professor Dr. Kiyotaka Nakajima. He is from the Institute for Catalysis, Hokkaido University. He received bachelor from the Department of Applied Chemistry, School of Science and Technology, Meiji University. And he received master and PhD from Department of Electronic Chemistry, Interdisciplinary Graduate School of Science and Engineering, Tokyo University, Tokyo Institute of Technology. He was awarded from the Young Scientist Award, from the Japan Petroleum Institute, and he received also award in 2014, Challenging Research Award from Tokyo Institute of Technology. He was also Young Scientist Award, from Catalysis Society of Japan, and in 2015 he received Young Scholar Lecture Award from the Chemical Society of Japan. Prof. Nakajima received his PhD in Science from Tokyo Institute of Technology, and in the professional career as a principal investigator from 2015, he was widely studied about the design of new catalytic materials and reaction for the production of platform molecules from biomass-derived sugars. Prof. Nakajima, now is your time to present your research.
Okay, thank you very much for nice, so kind introduction. And I'm very happy to be here again. So I gave several lectures in 2017 maybe. So at the time, Lina invited me as a lecturer. So, and I stayed here for a week, giving a lecture so to undergraduate and graduate student maybe. And this time, I will focus on our research activities briefly. But first of all, so in the morning session, so you enjoy the excellent and interesting chemocatalyst. And the first lecture in the afternoon, so focused on the biocatalysts, right? And again, let's go back to the catalyst, chemocatalyst again. So my topic is biomass conversion using heterogeneous catalysts. It's related to the chemocatalyst. And you know, how do you know SDGs, right? So it's very important topic. We will be chemists. Maybe you will be chemist, or you will be biochemist, or physicist, or something like that. Yeah. So your future will be related to some chemical activities or something like that, right? And we need to think about how to contribute to the SDGs contribution. And our topic is related to the number 11, responsible for consumption and production. And I confirmed by my Google, and I put Indonesia and SDGs on this homepage, right? And this is written in the local word, and I can't understand what they're writing, but the Indonesia, so has a lot of activities maybe for SDGs related, right? Maybe the Indonesia have some activities for conference and so on. And so one lady, received the award, right? So if you contribute to the SDGs activities, maybe you have a good future. So 2030, maybe Indonesia want to do something for SDGs. So please think about your future, in relation with the SDGs activities. And my research is related to, of course, this number 12, so responsible for consumption and assumption. Let's think about how to replace the fossil fuel resources with something renewable one. And it is biomass. Biomass can be obtained from photosynthetic approaches using CO2 and water, right? And that plant biomass is easily accessible. And there are a lot of biomass resources here in Indonesia, right? Food waste, agricultural waste, and so on. And due to heavy sunshine and always hot nature, right? We obtain a lot of biomass. You can utilize those for chemical production instead of maybe fossil fuels. But one negative impact in Indonesia is to obtain maybe natural resources, fossil fuel as well. So you need to change your mind. Let's think about sustainability. And in Japan, so of course we need to think about our sustainability. And Japan has no fossil resources, and we will import everything abroad. And so in our topic, we are focusing on biomass conversion using, so we identified this biomass resource as a renewable carbon for chemical production. And this is a typical scheme representing my talk. So we will use glucose obtained from biomass, and it is used for the chemical production to chemicals or fuels. This is important scheme. And there are a lot of agricultural product, byproduct. So in Indonesia, and you can make use of those. Those are almost fossil fuels in the future. If we develop this kind of conversion technologies, right? And we have two important issues here. So if we want to, decline the use of fossil fuels, one is energy, one is chemicals, right? But if we want to produce energy, we have several approaches already. So the photovoltaic, nuclear, power energy, and biofuel, wind geometry, and so on, right? If we develop the water splitting reaction system using electric power or sunshine power, right? And we can produce hydrogen and oxygen from water. And the combustion of hydrogen will produce a lot of energy. And after that, so the hydrogen is going back to the water. It's a circulation. It's a very green system. So we can find out any alternative strategy to produce energy, right? However, so we need to think about chemicals. All chemicals should be produced from carbon material. And we need to identify the renewable carbon source, right? And of course, one is CO2, and another one is biomass. And we have to think about what is the best for the short-term future and long-term future. And this scheme represents the material circulation. If we will utilize biomass as an initial primary resource and to produce chemicals, and so we can retain the current developed the society, right? But after combustion, after use, those chemicals should be going back to the CO2, right? The combustion. And CO2 can be utilized for the production of biomass again. This is circulation. But currently, we will use the fossil fuel resources. Its production, requests long time, more than 10,000 years, right? We can't, wait for long time to obtain the new fossil fuels. So we need to think about that. Direct utilization of CO2 is another option, of course. But CO2 is the extremely oxidized form of the organic compound, right? We need to reduce it. Reduction requires something reductant. Reductant should be hydrogen. Hydrogen is coming from fossil fuel now. We need to think about that again. So if the renewable hydrogen is easily accessible, maybe we can use CO2. However, another problem should arise. So CO2 concentration in the atmosphere is almost 400 ppm, 500 ppm. It is extremely diluted. We need to produce concentrated CO2 for large-scale production of chemicals, right? But it accompanies large energy consumption gain. We need another energy source, right? So this means that we have no idea to utilize such CO2. We cannot produce concentrated CO2 under the current circumstance, right? So we need a lot of technology, new technology, to overcome these issues. But if we utilize biomass, it is the accumulated CO2, different type of accumulated CO2. We rely on plant to accumulate CO2 in the atmosphere and utilize it as a carbon source, right? This is a very important concept in biomass conversion reaction. So we have no idea to accumulate atmospheric CO2, and we rely on the plant. So let's start the biomass conversion. So if we want to utilize the plant-based biomass, so it contains three important components: hemicellulose, cellulose, and lignin. So hemicellulose and cellulose are polymers of sugars, right? And basically, cellulose consists of the alpha beta glucose bonded through the alpha beta, a beta one for glucosic bond, right? So hydrolysis of cellulose will produce glucose. And if we can utilize glucose as a carbon source for chemical production, it is, of course, sustainable and renewable. And hydrolysis of cellulose and hemicellulose will produce C5 or C6 sugars, and those sugars can be utilized as a renewable carbon source for the production of the C6 to C2 compound as shown here, right? But cellulose hydrolysis requires acid catalyst, right? Acid catalyst means proton. So sulfuric acid, hydrochloric acid, and so on. But in the starch, the content is the same, right? Both of them are the glucose unit. But the starch can be easily hydrolyzed. You can eat rice and hydrolyze it. But if we eat wood, we can't utilize that, right? We can't decompose the wood in my stomach, in our stomach, right? So basically, it is not so easy, and we need to use acid. After hydrolysis, both of the reaction will produce glucose. And normally, cellulose hydrolysis requires the use of sulfuric acid, concentrated and diluted. This combination will produce glucose from cellulose easily. However, it is not sustainable because after the reaction, we need to recover the glucose from the reaction mixture. But if you use the homogeneous acid catalyst, we need to neutralize that. Neutralization will produce a lot of acid waste. It is no longer acid catalyst, right? And so we have to think about sustainability. We need to utilize repeatedly used and easily recoverable catalyst. And in this case, we need to utilize solid acid catalyst. And when referring to the previous works, this is one example, sulfonated carbon catalyst. So it contains the nano-sized graphene seed with sulfonic acid group can promote cellulose reaction in water. It is a solid-solid reaction. This is the reaction scheme. We added the cellulose powder and sulfonated carbon powder into water and start the heating treatment. And at the interface, proton, the immobilized on the carbon will interact with cellulose surface, promoting cellulose hydrolysis reaction. And after that, cellulose is decomposed, hydrolyzed into oligomer, and oligomer is again going back to the catalyst surface to promote further hydrolysis reaction, producing glucose or small oligomer. And when prolonging reaction time, we will convert everything and obtain the sugar solution, right? And sugar solution can be replaced easily by decantation or filtration treatment, and remained catalyst can be used for the next reaction just by adding the new cellulose source and water, right? It is easily circulating. So this concept, is suitable for the number 12 SDGs concept, right? So please think about the use of heterogeneous catalysts is very important for realizing the SDGs. So low energy consumption, less waste, and high reusability, right? It is very important for the system. And after hydrolysis of cellulose, we can utilize glucose, right? And how do we utilize glucose? One idea is shown in this slide. So the glucose can be converted into HML, 5-hydroxymethylfurfural. This compound have two functionalities, hydroxymethyl group and formyl group, at the center of the furan ring, right? And if we convert these two functionalities to carboxylic acid, alcohol, amines, and after the ring hydrogenation and the ring opening reaction, we obtain linear compound as shown here. Those compounds can be used for polymer application, right? bifunctional compound can be used for the polymerization reaction basically. And if we develop this scheme, so from glucose via HMF and those compound, we can utilize the glucose as a source for the production of chemicals and fuels, right? This is an important concept. And our group focus on the production of fuel and dicarboxylic acid, this shown here, right? To the carboxylic acid group were attached to the furan ring. And polymerization of FDCA with ethylene glycol will produce polyethylene flavonoate, as shown here. This is very interesting polymer. So in this polymer, the center of the network is the furan-based unit. It is a kind of replacement of the terephthorate produced from the oil. And this is a replacement of oil-based terephthoric polyethylene terephthorate. And so this PEF, polyethylene flavonoate, have very excellent and interesting properties, mainly for the gas barrier. Let's compare bio-based PEF and petroleum-based PT. And bio-based PEF has excellent gas barrier property to oxygen and CO2 and water. This means that if you put water inside the PEF bottle, you can protect it against oxygen and also CO2 or something like that due to low gas barrier, high gas barrier property. So the attractive future will make this polymer much more attractive as a replacement of oil-based PT. And the potential application is quite wide: beverage bottle, film carpet, clothes, and so on. And total amount terephthalic acid consumed for PT and PBT production is almost 80 million tons in a year, with annual growth rate of about 7%. So this means that if we replace everything terephthorate-based polymers with bio-based one, so we can contribute to CO2 reduction. And how do we reduce the CO2 emission by this concept? So this scheme, so the graph explained that. So this result was reported in Nature Sustainability paper in 2020, explaining that the 1 ton of PT produced from oil accompanied the formation of 4.5 tons of the CO2 emission, right? This means that a large amount of CO2 is produced in this process. However, if we produce PEF, so CO2 emission is quite small. So about 2 tons of CO2 is produced in the PEF production. It's about half, right? So this means that we can reduce the CO2 emission if we release a lot of PEF in our society. So this is the evidence to the motivation to promote this research activity. So PEF has very attractive future, but it is not commercialized yet. This is a result of 2021, so confirmed by European Bioplastic Association. So this graph summarizes the total amount of bio-based plastics. So right hand and left hand, so distinguish the part for bio-based and non-biodegradable, biodegradable, and so on. But anyway, so please focus on the PEF. You can see 0.0%, right? This concept was established a long time ago. However, so PEF is not commercialized yet, right now. So this means that we have some technical issues that hampers the commercialization of this PEF. And I will summarize the current problem of PEF production. So the above scheme explained the conventional approach to FDCA, the main unit of PEF. So FDCA can be produced from glucose. Not glucose, it is fructose. You know, fructose is expensive sugar produced from glucose by fermentation reaction, right? So this means that cost, intense resource compared to glucose. And abundance is not so high. Of course, glucose is much better. And once we obtain the HMF, HMF can be used only in diluted reaction solutions. If you utilize this HMF in concentrated solution to increase in the productivity, this accompanies a lot of byproduct formation due to the presence of two functionalities, alcohol and aldehyde, in the same molecule. This is a very big problem. We have to use diluted reaction system to obtain FDCA, but that requests large amount of solvent and large reactor if we are focused on the large scale production. This is a very big problem. So we decide to start the new project with an industrial partner, Mitsubishi Chemical Corporation, to establish a new process. It is explained in the bottom. So we utilize glucose as the main starting material to synthesize the HMF. Once we obtain the HMF, we can't use it as it is. We will protect the formyl group with 1-cypropandiol asterization reaction to prevent side reactions. And we will use HMF asterization here for FDCA production. And we obtain very excellent result. I will summarize this talk. So these results in this talk. Let's think again back to the total process of the FDCA production. So cellulose hydrolysis will produce glucose. And as I explained, so the same solid acid catalyst can be applicable for this reaction system already. And glucose conversion to HMF is another topic. And one more topic is the oxidation of HMF to FDCA. We will briefly explain that. So the acid catalyst can promote the dehydration reaction of glucose to HMF. However, most of branched acid catalysts require very high reaction temperature to obtain HMF, so that accompanies a lot of byproduct. However, recently we found that some Lewis acid catalysts will promote the HM formation from glucose selectively after phosphoric acid treatment of something like that. For example, titanium, niobia, and so on. And we obtain relatively very high yield. And we published a lot of paper about this topic. And if you are interested in, refer to those. And based on the second result, so we will obtain HMF. And let's think about HMF oxidation. First of all, so I summarized most of the representative papers reporting the HMF oxidation to FDCA. You can see mainly the supported metal catalyst, platinum, ruthenium, and gold, can be applicable for this reaction. In the presence of oxygen as an oxidant, right? Metal nanoparticle will activate oxygen to promote oxidation reaction. You can see excellent FDCA yield in this table. So most of them are more than 90%. Of course, everything very excellent. However, let's think about the HMF concentration. Everything, so lower the less than the 2-8% mainly, right? So processes using diluted reaction solution cannot be realized in industry. So to increase in the product, we need to utilize more and more concentrated. So this is a very big barrier. And we try to examine this problem. We have to first confirm what's happened in this system. And we identified gold cellular catalyst. Cerium oxide has gold nanoparticle in average size of about 5 to 6 nanometer. And we will use gold cellular for oxidation reaction. You can see in the TM image that the black dots are distributed on the metal oxide support, and those black dots are gold nanoparticles. And we will use this for the oxidation reaction. And this is time courses for HMF oxidation reaction. First of all, we will use HMF. But in this case, 10 weight% solution, right? We simply increase in the concentration up to 10 using most active catalyst under the common reaction conditions. And you can see decrease in HMF line, right? Black line, and also increase in byproduct at the first stage of the reaction. So this means that and it reached about 70%. If you obtain something about 70%, it is a main product, but this is byproduct, right? And FDCA yield is about 30%. It is quite low. So this means that it cannot work. This catalyst cannot work for 10 weight% solution. However, we think about what's happened in this case. Kinetic studies explained what's happened, right? So we estimated the reaction rate constant of each reaction steps, right? In this case. However, first desirable step, so shows the 0.5 H minus, right? But byproduct formation rate is 1.1, twice more. This means that byproduction formation is predominant in this system. And we have to suppress this byproduct formation, otherwise we cannot obtain the FDCA. And another concern, our catalyst is not good, simply. And we confirmed the reaction using diluted reaction system in the above, so 1 weight% solution. And we obtained excellent yield. This means that our catalyst can work, but our catalyst cannot work in 10 weight% reaction solution, concentrated reaction solution. This is a problem. And we identified the source of byproduct. It is a formyl group. We protected formyl group, for example, dimethyl ester and 5-member ring ester with ethylene glycol, or 6-member ring ester with 1-cypropandiol, and examined those compounds, so the thermal stability in NMR tube. So this is a degradation phenomenon, right? 1 hour, 2 hour disappears immediately. Dimethyl ester, almost the same. But 5-member ring ester show a relatively good activity, good stability. But 6-member ring ester can retain as it unchanged as it is, right? As shown here. This means that introduction of the 6-member ring ester into the HMF can increase in its stability. And we decided to utilize it as a starting material for FDCA formation. And we examined the oxidation reaction of HMF and PDHMF, propandiol protected HMF, under the same reaction conditions. This table summarizes the reaction result under different reaction conditions. Entry 1 and 2 utilizes the diluted reaction solution, 1 weight% solution for HMF and PDHMF. The result is the same, almost the same, right? However, once we increase in the concentration up to 10, entry 3 and 4, so the result is largely different. HMF will give the 28% of FDCA, but PDHMF will produce 80% of FDCA. This is due to the difference in the stability. And after optimization of the base amount, so we will obtain 94% FDCA yield in entry 9. And this high yield can be retained in the case of 28% in entry 7. This is our, and those high yield is due to the stability of the PDHMF, because entry 8 and 9 explain that. So those reactions were conducted in the absence of oxidant. This means that if HMF and PDHMF decrease, so this means that degradation. So conversion, let's compare conversion. So HMF is gives the 47 conversion. This means that it's degradation, degraded. But the conversion of PDHMF is only 2%. This means that PDHMF is stable under the reaction conditions. So time course line for oxidation reaction of PDHMF under the 10% solution under the reaction conditions. So the reaction proceeds as shown here. Hydroxymethyl group is oxidized to formyl group, and the formyl group is oxidized to carboxylic acid. This is the first and second step of the reaction. So the reaction rate constant is not so small. However, final reaction step, so converting the 6-member ring acetal to carboxylic acid, this is a rate determining step with the reaction rate constant of 0.15, 1/10, right? This is the rate determining step. And we analyze what's happening in this case. Of course, we can't detect any intermediate and so on. So we simply relied on the DFT calculation to predict what's happening on the catalyst surface. So reaction starts from the activation of cerium Lewis acid site, so to the acetal moiety, forming hemiacetal intermediate IM2, right? Hemiacetal intermediate is oxidatively dehydrogenated to form the carboxylate, as shown in IM3. This is a desirable process. And after hydrolysis, we will produce FDCA. However, one more different route is expected, so via TS3 to IM4. This is energetically unfavorable, so we concluded that the IM1, IM2, and IM3, this pathway is preferable compared to the other pathway. So I summarize the first part of my talk. We can utilize 20 weight percent solution to synthesize FDCA using gold Celia catalyst. This is our achievement, and this is interesting result of our talk. And the rate determining step is the carboxylic acid formation from 6-member ring acetal. And the main reason to obtain such high FDCA yield is due to the use of acetal protection strategy. And recently, we developed continuously the process to obtain the best monomer for PEF production. And recently, we employed oxidative esterification to synthesize FDCA methyl ester. And the bottom scheme explains the latest result. We designed stepwise approach. First step is the oxidative esterification of hydroxymethyl group, so methyl carboxylate in methanol using 20 weight percent solution, and also gold Celia catalyst. After the PD-MFFC formation, we remove the protecting group, FP propanediol, and we obtain the MFFC. This is a very easy step based on the organic reaction textbook. And so we oxidize again the MFFC in methanol to obtain MFDC. This is the overall yield is 91%. And we can suppress the decomposition of PDO, and also we can guarantee the high productivity, and also we can reduce the use of the amount of base. In the previous reaction system, 200 more percentage, but in this case only 7.5 more percentage. And we explored this reaction strategy, so to other molecules, including diamine and amine carboxylic acid, diol, and so on. And recently, we developed diamine formation system. This is based on the selective oxidation from PDHMF to diformylfuran HMF, diformylfuran acetal, as in the bottom, in the left side of the bottom scheme. And next, reductive amination of the DFF acetal, so using cobalt-2p nanorod catalyst to obtain the diamine compound like this in very high yield. So we confirmed acetal protection strategy is very important and effective for converting HMF-related compound to desirable product. And this is the final slide of my talk. So let's compare our achievement in the reductive formation. Stepwise reaction. So first step is the reductive amination, the converting the formyl group in the left hand and to amine, and the next step is the conversion of the 6-member ring acetal to amine, giving in total yield about 89%. This is quite high, using 10 weight percent solution and 10 weight percent solution. When referred to the previous paper, one paper, find one paper, so in green chemistry. So they adopted also the protection strategy, but this is imine protection strategy. So they obtained also very high yield using 1 weight percent solution. But when they increase in the concentration up to 10, yield decreased to 75. But our process can retain high yield, right? In both diluted and concentrated reaction solution. So our result is simply comparing the acetal protection versus imine protection, and acetal protection is much more effective for concentrated reaction system. So the summary and the future perspective. So we developed this acetal protection strategy for the production of essential chemical from biomass, mainly for the HMF based. And we have 3 collaborators, Professor Hideki Kato at Tohoku University, and Professor Emil Hansen at the Eindhoven University of Technology in the Netherlands, and also Takato Mitsumi at Osaka University. We collaborating catalytic development and DFT calculation to establish the new biomass reaction, conversion reaction system. Recently, we studied direct conversion of glucose to C2, C3, and C4 compound in combination with the acetal protection strategy. And those fragmented compounds can be used for the production of ethylene, propylene, butene, butadiene, right? Essential base molecules obtained from oil. So this reaction system is also important for the future biomass conversion reaction. So based on my talk, please think about what do you want to do a chemist in the future? And also how do you contribute to realizing SDGs, right? Everybody should be working in something in chemistry related process or something like that, right? And the maybe future perspective should be simply relating to the SDGs. And my research activity and my life work is related to, of course, biomass conversion, but keyword is heterogeneous catalyst and renewable resource and biomass conversion reaction. This is included in the topic 12 in SDGs. And finally, I have to thank all the collaborators and group members. My group has 2 important staffs. So Dr. Satoshi Suganuma, Ryota Osuga, so associate professor, assistant professors. And 2 guys, so they are Jan Wisfeld from the Netherlands, Nirupama Seat from the India. So they conducted mainly for oxidative esterification and also reductive amination works. I have to thank the 4 other collaborators, especially for Atsushi Fukuoka, my previous boss, and also the industrial partners. And my laboratory was established from 2022, so April. Our laboratory is a young laboratory, but the total member is increasing, and you see a lot of overseas members. Recently, one lady was coming from Oman. So we are welcome to join. We are very happy to accept the student from also Indonesia. Okay, thank you very much for your kind attention.
Thank you very much, Prof. Nakajima, for the nice talk. Now please sit down in front of to answer or to discuss about this topic or some question from the audience. And from the students, please ask, or if you want to know about the or maybe the study or opportunity in Japan, you can raise your hand and mention your name. You should not ask only about the chemistry, but you can ask also about the opportunity to study in Japan, I think, to be more interesting this meeting. Nandi, do you have question? Or maybe Faki? Prof. Akira Onoda has talked about the biocatalysis. Yeah, it's related to metal complexes and then related to enzyme. Yeah, and it was used for catalytic reaction. Yeah, in biomimetic, I think, or it's tested for several kind of reaction like polymerization and so on. And Prof. Otomo, yeah, he spoke about the biomass catalyst using inorganic compounds material, especially for metal oxide. Yeah. Oh, ini Prof. Nakajima. Oh yeah, Prof. Nakajima. Yeah, sorry. Any question from the audience? Yeah. If no, I will ask.
Okay, thank you for the time. My name is Nandi from Chemistry Department. Thank you for the presentation about biomass conversion and biocatalysis. First of all, I want to ask to Mr. Nakajima, Nakajima Sensei, about the biomass conversion. In Indonesia, this topic is rising attention because renewable technology and renewable renewable things is being researched on. What I want to ask is about lignin. Lignin in wood, sawdust. Lignin from sawdust can it be renewable polymer building blocks from lignin?
Okay, so you mean soda lignin, right? Produced in the paper industry.
Yes, many application, but usually it's for paper industry.
So virgin lignin can be obtained by chemical process recently, yes, and without any degradation. But the lignin obtained in the paper industry is largely degraded, change its structure, and the lignin, lignin boiler. Lignin boiler means that after the processing in the paper industry, they obtain a lot of lignin, and lignin is a source of heat. So for the paper industry again, and so this is highly efficient, and lignin can be utilized currently as the energy source in paper industry. However, we have to focus on the lignin, of course, the chemical resource for the material production, something like that. However, based on the previous papers, so the processing of the depolymerization and the production of particular monomer from lignin is very, very difficult. So the structure is very complicated, and we cannot focus on one simple the resource. And in terms of that, lignin utilization is quite high level challenge. And in that sense, we decide not to do lignin conversion. Of course, in the future, but first of all, we need to think about what is the main, so the unit obtained from lignin. We have to identify that. Otherwise, let's degrade, let's depolymerize lignin, and let's see what's happened, what kind of product we obtain. That is not the good idea, right? So it is important, okay?
Okay, thank you, Mr. for the answer. Okay, for the next question, I would like to ask Mr. Onoda. Onoda Sensei. Actually, my focus research is not biomass and biocatalytic. So my question may be too broad of the topic. So, but I want to ask anyway. About in your presentation, you give an example myoglobin with a heme. Nah, my research is around the topic of oxygen reduction, which sometimes use metal complex like heme itself. We using iron porphyrin, which have similar structure as heme itself. Nah, what I want to ask is within the protein apa yang bilangnya tandem catalyst, can the metal complex for the protein combination is used for the catalytic reaction, including the oxygen reduction? Thank you.
Oxygenation reaction.
Yeah. Oxygen reduction. Oxygen reduction.
Oxygen reduction.
Yes.
Oh,
oxygen to form
O2
water.
evolution.
Yes.
Yes. Of course. Oxygen reduction reaction. For example, some of the enzyme can do the reaction containing the He in the protein, and also the porphyrins or particularly for the electrochemical reduction, oxygen reduction reaction is pretty well studied.
Yes.
Right? Yeah. I also work on this one example. I burned the myoglobins, and we have some iron site that contains nitrogen and graphene. So I think it's a really good target for the reactions, right? But it's quite what kind of target you are focusing?
The target is usually increasing the efficiency of the reduction itself, because oxygen reduction can do two pathways. The first one is the 2 electron pathways, and the other one is 4 electron pathway, which is form water, and it's more efficient. More efficient if it's go to the 4 electron pathway.
Right.
And usually we use metal complex and carbon support for the catalyst. This is the material catalyst. But if we are going to use maybe the biocatalysts, are the protein can increase the potential electron exchange in the reduction itself. Maybe like that.
Right, and so the metal complex is well platformed to design, right?
Yes.
For the metal surrounding by ligands, but most of the problem for the metal complex to do the electrocatalytic oxygen reduction reaction is the path for the electrons, right? Conductivity is not that high in most cases. So I think you need some tricks to overcome that, right? Some group have tethered some linkers for the conductive materials. That would be the possible idea, right? But I think the combination, or I don't know, somehow that just mixing or hybrid or more well designed with the covalent, embedded with a covalent framework with the graphene material will be great to increase the conductivity.
Okay, thank you. Because the reaction itself is in our blood, where the heme is absorbs the oxygen and then converts it into the carbon dioxide in our body system gitu. So maybe using the biocatalyst as an enzyme maybe is going to be more effective, or it's my hypothesis.
All right, all right. So you want to ask about in general point?
Yes.
What is the advantage of biocatalysis?
Yes.
Right. I mean, so let's see. I mean, in general, I mean, the biocatalyst is quite effective for specific reactions, right? So one example for it is still quite limited for the large-scale production. One very unique example is which is developed by Mitsui Chemicals for the production of acrylamide. This was done by heme-containing enzyme, right? I think that it's a largest amount in the global market. So if you find a specific enzyme for really efficient for specific reaction product, so the biocatalysis is better in some cases, right? Of course, you have to produce, right? And of course, but the problem is you have to purify the enzyme, then it costs a lot. Then you have a whole cell catalysis, right, without purification. This also, some cases works, but it not works perfectly. And then also, if you do the whole cell, also the problem is how you, manage the waste as well, right? And then, so the balance of, and then the difficulty in the biocatalyst. But the advantage is you can work with the, mixed starting materials, right? For example, the lignin, enzyme, some of the manganese peroxidase will break down the lignins. So even though there's a bunch of mixtures, so, but the problem is that be in a economically efficient, right? As a business or not, other factors. I think, of course, I would try to always find out the good candidate that was successful in the market, but yeah, that's, also the advantage is we have a huge variety of enzymes in this world, right? Just we don't know. So we can screen out, we can find possibly more effective and robust enzymes.
Okay, thank you for your answer, Mr. Ya memang, ya memang harus dites dulu ya, Bu. Ya, terima kasih, saya kembalikan, Bu.
Thank you, Nandi, for the question. Any other question from the student from this side? Maybe Chitra. I saw my student Chitra working on hydrolysis of cellulose. Of this hydrolysis using solid acid catalyst, because it can be innovative for the next research sawit. We have grant for student and for a lecturer from our ministry from palm oil. That the competition is almost every year or 2 years. That's why this approach will be very nice if we can propose to the Grand Summit the next year or the next 2 years. That's why we can learn from Professor Nakajima how is the efficiency of hydrolysis using solid catalyst or solid acid catalyst. And have you compared if we use, for example, sulfonated zeolite or sulfonated mesoporosilica, something like that?
Yeah, so the sulfuric acid is not stable. So if we immunize it on the conventional acid, the support, the metal oxide support, for example, silica cannot stabilize sulfuric acid, and also the zeolite are the same. So zeolite has acid site, right? So we have to make use of those acid site, original acid site for original material. And in this case, so of course, other candidate are carbon catalyst, without sulfuric acid. But the carbon catalyst has carboxylic acid. But due to weak acidity, so the reaction system requires very high reaction temperature, 180 to 220, so to promote the reaction. But we can hydrolyze cellulose with the bare carbon material. So it is reported by Professor Fukuoka, so in Japan, and so we can think about other catalyst candidate, but we have to think the other sulfonic acid catalyst. So other than sulfonic acid catalyst, because sulfonic acid is simply stabilized maybe only on the carbon material. We have no other candidate maybe.
And how about the condition or reaction condition? How high the temperature, for example, or the pressure, and do you use also solvent for that during the conversion?
Because primarily we have to use water. Yeah, and the reaction temperature is I said 180 to 220, but in the case of sulfonic acid carbon, so the reaction temperature is 100 degrees C. It's quite low, but we have to use the autoclave reactor, and we do not need the pressurized something treatment. So due to no relationship for the hydrolysis reaction, but the increase in the reaction temperature will increase the pressure, inside pressure, right, of the reactor, and that is the basic concept to design, to choose the reactor, the type of reactor.
Yes, thank you. And in the case of cerium, you use cerium oxide here as a support for oxidation reaction, that you use also gold nanoparticle. In this case, why did you choose cerium oxide here?
Cerium oxide is preferable for redox system. Cerium oxide can release lattice oxygen, and it is involved in the oxidation reaction. It's one benefit. And of course, there are a lot of papers about the support of the gold nanoparticle, and among them, the cerium is identified as the best support for oxidation reaction, especially in this case.
Yes. How about the surface area of this metal oxide? It has a great influence.
70 square meter per gram. It's not so high.
Yes, because I have idea maybe for the next my student will prepare about cerium bismuth, and then we can support with some kind of metal and do the similar reaction like that. Maybe will be faster or more effective. We will see. Yes, thank you. Any other question from the student?
Okay, good afternoon, everyone. Good afternoon, Mr. Nakajima. My name is Chitra from Chemistry Department. You said before in the presentation, using carbon sulfonated catalyst can hydrolyze cellulose become glucose. Is it possible to using carbon sulfonated catalyst for hydrolyze the lignocellulose until cellulose only, not continue hydrolysis into glucose? Because in my research, we only want the cellulose, not until the glucose. Is it also possible?
Okay, you mean you want to remove the lignin and the hemicellulose?
Yes.
Hemicellulose can be easily removed by heat treatment of the lignocellulose biomass in pure water at high temperature.
Yes.
It is easily soluble in water at high temperature, and you can easily remove hemicellulose first. And
okay.
About lignin, and please refer to several papers from Europe. So they synthesize, they want to use lignin as a source for chemicals, and the lignin first process is reported, meaning that the palladium carbon and the metal trifluoride mixture in water, and in addition to the lignocellulose, will remove only the hemicellulose and lignin only, and the remaining solid contains simply the cellulose only.
Yes.
So maybe you can use that technology to obtain pure cellulose.
Okay. Next question, Mr. For the cellulose, I mean that I want to have a nanocellulose. So we used to reduce the size using hydrolysis. And what I do in my research is using hydrochloride, and it use hydrochloride so many milliliters, and also we have difficulties to denaturalize. It also what I wanna ask you is it possible to use sulfonated carbon catalyzed for hydrolyze the cellulose become nanocellulose? Maybe that's the question.
Okay, so it's very difficult, of course, because reaction happens from the surface, right? Hydrolysis reaction happens from the surface, and nanocellulose mean that you have to stop the reaction on the half, right? And we have currently no idea because the resulting nanocellulose cannot be simply evaluated. For example, the amount of sugar can be evaluated by HPLC or HPLC, right? And we can calculate conversion. But you want to focus on the amount of nanocellulose, right? And the first problem is how to evaluate nanocellulose itself. You have to dissolve that into some solvent and think about the polymerization degree, right? And it is one barrier and another barrier. So the reaction cannot stop on the halfway if you use solid catalyst or something like that. So of course you need some trial, but currently I have no idea to control that. Okay.
Yeah, okay. Thank you, Mr. Nakajima.
Thank you, Citra. Any other question? Pertanyaan lain, saya bahasa Indonesia juga nggak apa-apa. Ini dari mahasiswa apa? Kimia. Oh, pendidikan kimia. Chemistry education. Maybe for the new student that's still in the second semester or third semester. Second semester. This is maybe new insight for you that chemistry is very broad range of science because the chemists can do about biomass conversion, can do about the biocatalysis, and this is how you should learn. In the future, you will see, oh, chemistry is very interesting actually. Yes, not only about like lecture and so on, but the application is very large. Yeah. I have one more question to Prof. Onoda, Prof. Akira. You have like some technique to link between the metal complexes and with enzyme or protein. How is the strategy and how is the stability of your catalyst during the reaction? Because it looks difficult, I think. And if we compare, for example, if we immobilize the complex or in the enzyme in the solid state or in the porous material, how is the stability compared to this protein?
Okay, so the question is, can we, not only for the reaction I showed, but in general, right? In general, if you immobilize the enzyme, what happens? Of course, there's a lot of applications when you use the enzyme immobilize simply silica or many applications. In some cases, we can just simply buy the enzyme immersed with the silica, and some of the enzyme is really tough enough, even though dried in some cases. So and then they are active, but I would say it really depends on the enzymes, right? And then it really depends. So that's why many works is going on. So and also if you immobilize with the non-covalent interaction, the enzyme will be released, right? Right. So you have to link. So that's why there's many examples that link the protein with the aldehyde, with the lysine on the surface. So the problem in this case is we don't know how the enzyme is oriented, right? It's really random. So I didn't show it today, but to overcome those problems, we developed N-terminal specific modification. So really position specific chemical modification. So then you can make the enzyme quite alive, right? If they are sticking everywhere, so the enzyme will be not comfortable, right? So yes, so if you have a suitable, you choose the suitable option to immobilize, link the enzyme to some kind of support. So the enzyme is quite, fine. They work well, right? But I mean, you need some, good option to do that. Is that answer your question?
Yeah, it's mean during the catalytic reaction, we should handle it under inert condition, yeah. During the catalytic reaction, catalytic test for your type of catalyst, should we handle in the inert condition? It is air stable or not, something like that. Is it air stable? Air stable for during the catalytic reaction?
Right. It really depends. So I did this reaction is air stable. I choose the air stable reactions, but some of the enzyme is very, very unstable in air. For example, if you some of the protein isolated or expressed in anaerobic bacteria, for example. So deep, some of the bacteria very deep in the sea or deep in the ground. They don't need oxygen. They really hate the oxygens. So the proteins work in those bacteria. They're easily decomposed in some cases. So you have to do the reactions in inert atmosphere. So, right.
Yes, thank you. Any question from the student? Maybe do you want to ask about the opportunity for scholarship in Japan? Some of the students are master, some are bachelor. Maybe just short comment how to fulfill the requirement, or how can be the student pass the qualification for Japanese scholarship. What is your
Pardon? Once again.
What is the tips for the student to pass the qualification for the scholarship in Japan, so they can be more motivated in the study, something like that.
Okay, scholarship to, I don't know, but first anyway you should contact earlier probably with some PI you want to join. Right. Then I think that's the big point, because in my experience, of course, I have some email from some students in some countries. I try to at least communicate with 2 times in online interview. But the difficult thing is some of the part I cannot share sometimes, right? Because of the project is still not ongoing, right? So we have to choose it takes some time to choose the project, and also we need some time to understand what kind of background the students has, right? So I think I don't know the good tips, but you have to communicate earlier, and then you have to
maybe for the language should be the TOEFL score, for example, or IELTS score.
Of course, the grades in academic scores, also the English scores, because most of the students is really qualified very well, right? So I don't know that any other choice to evaluate. Of course, the project might be some point, but of course the grade English scores would be, of course, very important, right?
Yes, thank you, Prof. Akira.
My pleasure. Yeah.
Yes, thank you. Any other question? I open one last question for you. Ada pertanyaan nggak? Maybe you want to ask something. Kalian paham nggak yang diterangkan? Masih dikit-dikit. Ya nanti harus sering ikut acara seperti ini biar pemahamannya lebih. Terus sering baca jurnal, bisa sit in di kuliah kakaknya. Yes. Now it's already 15 o'clock, yeah. It's enough, yeah. I think the research talk today is very great, and we have very full information or very valuable information about the current research in Hokkaido University, which is very suitable with our research field actually in our university. And hopefully in the future we can do like further collaboration about that, yeah. And for the student, it will be also very important for them that chemistry is very interesting. This is the key point, yes. Once more from me as moderator, we acknowledge very much for this event, and we give applause to all the speakers, students, yeah. And we can come back again. And to close the session, maybe we can do photo session, the last photo session, because the audience is different here. Yes, yes. And I will close the session by this photo session. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon.